Okay, but there are, of course I can look at something in nature, something dynamical in nature, and try to learn dynamical rules from there. Okay, that is what scientists have been doing for ages. These days, of course, we simulate a lot, right? And you might think, okay, if you're simulating, you know the rules, right? But you might actually like to know, even out of a simulation, if you see some dynamics, are there some simpler rules, right? So for example, if you simulate a lot of particles banging into each other, you know all the rules for how the particles evolve. But you might see that in long time, what you can predict is how the density becomes constant around the place. So there could be collective variables which you want to, which has much simpler rules, and you might want to learn that kind of rule. So and as I already put out in this example, it's related to the second point, which is that there could be these kind of variables which have greater predictability and simpler rules that you might want to discover, like collective coordinates in the system, right? Okay, and the last bit is more engineering than science, but scientists use it all the time. You might not only want to learn the rules, you might want to manipulate systems with the rule. You most probably want to move a robot through something, or have a quantum system be put into a certain state starting from another. Okay, so you want to control it. And in many cases of controlling the system, especially when data acquisition has delays, or it is noisy, or it is rare, you might actually do well to learn some approximate model of the system, okay, so that you can manipulate the system accordingly. So these are some of the major reasons why we want data-driven models, simpler models out of dynamic data. Okay. So I'll try to do this talk in 3 parts. And so the first part is sort of a probabilistic formulation of the problem. That's what, like, from the 60s, 70s, 80s. Okay. Then I will go to part 2, which is what we have gotten very excited about, our ability to use feed-forward neural networks. I understand that yesterday you had a lecture and tutorial on deep nets, right? So you're familiar. I mean, it's very hard not to be familiar with it, even if you don't practice anything. Newspapers are screaming about it. Okay. So, and how can you use that, right? And again, very overview level. And the last bit I want to say is something about how tapping into a high-dimensional space, right, sometimes simplify things, right? And that is to do with dynamic mode decomposition. So let's see how we go through it. At the end of each part, I will stop and I'll invite some questions. I know it's difficult to extract a question from someone who's thinking I don't understand, right? But please, most of the time, I'm not very sure what is on there, okay? I have confusions. So you should have confusions too, okay? Okay. So the probabilistic function, I'll talk about sort of time series with Markov models, latent variables, state estimation, learning the thing, and systems neuroscience application that actually involves Yavash there, okay? I have to definitely pay my homage to him. And if Domenico is getting upset, the next 2 examples would be about the work I was lucky to do with him. Okay, fine. Okay. So, time series data. So I'm going to call our observations Y. Okay. Now, most of the time when physicists are seeing something like fluid flow or measuring some or observing some, I don't know, smoke move through something, right? They have some high-dimensional vector representing the state. Okay. Or at least their observation. They have lots of sensors measuring something. So you think of this y1 colon t as a bunch of vectors, each of them, let's say, n-dimensional. Okay. Now, many of these methods actually doesn't require a vector with numerical entries. Okay, y could be a categorical variable. In fact, some of the most useful applications of the methods I'll talk are to DNA sequence data or to languages. Okay, but I'll pretend these are numbers, and it turns out that in many of those problems, sometimes it helps, especially modern day natural language processing problems. It helps to convert words into vectors too. Okay, so in some ways, thinking of these things as numbers and not as discrete stuff, okay, it's not such a bad thing. Okay, so I have a bunch of vectors. Okay, I called it capital T, and I'll keep on changing notation because if I need to transpose, the T will be taken, etc. But right now, 1 to T. So it's a time series, right? Okay, and I can say, oh, I'll make a probabilistic model of this data. Okay, this is is there a way of sort of pointing? Oh, maybe I should point here. Right? Can you guys see my cursor? You guys can, right? Okay, so here is the joint probability distribution of all these y's. Okay, and the point is that because of the beauty of how you can always do conditional probability, you can always write this as probability of y1, then probability of y2 given y1, probability of y3 given y1 and y2, okay, all the way till the end, right? And okay, if I ever try to write down something like a dependency graph, it will be y2 would depend only on y1. y1 is the beginning of everything, right? It has a probability distribution, the marginal probability distribution. And as you go further, more and more things from behind keep on affecting it, right? So on one hand, you look at it, so, oh, so cool. I can always write future as a function of past, right? But the trouble is that it is so general, it's almost useless, okay? You can actually do it backwards in time, okay? The fact that you have this many parameters to learn, it's like learning the most general probability distribution, okay? And that we know by seeing just one data point, one time series or a small number of time series examples. It's pretty hard to learn, okay? And if you're getting a hang of how this school goes, you'll most probably sense that what one is trying to say, that we can do machine learning when there is some structure in the data. If you give me random data, I can't predict or make any sense of it. I mean, my algorithms can produce an output, okay? But that's about as much as that's garbage, right? So we often try to say, I assume this problem has some structure, okay? So one kind of structure you can say is that the yt depends on no more than k previous things, right? So easiest would be if it was 1, right? So this would be some kth order Markov model, okay? Future y gets predicted by the string of y's before, but it doesn't go all the way to the past. And you have most probably seen examples of it in terms of like autoregressive models, okay? Where yt is a linear combination of yt minus 1 up to yt minus k plus some noise, okay? That kind of time series fitting is the basis of lots of, if immediately somebody wants to project, I don't know, stock market, etc., etc. This is the first idiotic thing you might do, right? Okay, so that's one way, okay? Try to remember the effect of past through only a short window, okay? A limited window of past, right? But there is sort of an alternative. The alternative is, so this is, again, if you have seen it, okay. How many of you have actually, maybe it's time for me to break your silence. How many of you know about hidden Markov models? Okay, so you guys, okay, unless you see me saying something grossly wrong, okay, we'll keep your cool, okay? And I want the guys who have not seen hidden Markov model before to ask me questions and see get something out of it. Okay, I'm sure that's quite a possibility that there will be something grossly wrong, but then please correct me because otherwise I'll fall down. But okay, so in the hidden Markov model latent variable, the idea is the following. Okay, there are some secret variables in the world. Okay, and those secret variables determine what we observe probabilistically. Okay, right? So, and essentially what we want to know is to get to these secret variables. They're a little bit like our collective variables in physics, right? We want to say, I see a lot of things, but actually just because it's ferromagnetic and there's a magnetization under that, right? Now, I said something about stock market, because the stock market is close by. But anyway, even if you want to know about the economy, you might find some sort of data. I don't know, employment here, okay, general income level somewhere else, etc., etc. The real wheels under it may be new technology innovation, maybe some sort of recession versus, okay, some bull or bear market dynamics, which we don't get access to. Nobody tells us we are in this type of market, right? Of course, everybody tells us, but different people say different things. Okay, so there could be some sort of underlying macroeconomic dynamics that's going on, right? And what you're observing are some indicators out of it. So it makes sense to say there is a fundamental model. What we observe is some sort of stochastic function of it, right? And our job is to sneak back from this stochastic function, from these observations into these secret variables. Okay. Another way of thinking about it is that if so the way this model works, I have written down equations but ignore equations. Somebody tell me if chat has anything screaming something at me. So this is a hidden Markov model because these hidden variables, they have probabilistic rules of transition, right? Okay, and these hidden variables kind of emit these observations. Okay, right? So if you think that way, you should think when we have some data, okay, these y's are pinned down. Okay, I've seen this, but I don't know the secret underlying thing. There's a whole probability distribution of them. They could still wiggle. Some with high probability, some with low probability. If I had a Monte Carlo way of doing things, I could have sampled it, right? Right? And in that view, right? So this type of model, okay, is very useful. One of the reasons it was quite popular sometime and even now to some extent is that when people wanted to do speech recognition, people used to use hidden Markov models where essentially the sounds I'm making from waveform, you could figure out some features. And these features were, you can see the feature, right? But secretly, I'm trying to produce some phonemes. And then there is some transition structure of these phonemes, right? So a hidden Markov model could capture that and perhaps do word recognition with something on top of it. Okay, yeah.
Maybe that's a very general question, but what's the general definition of the Markov model?
Okay, so I am, being a physicist, I want to say everything is a hidden Markov model, but okay, let's give a definition to that and satisfy you. Yeah. You can write on the wall using. I'm told, right? So I'm very nervous about writing on the wall, but I was given a demo. Okay, so I'll do this. But okay, so look here, there is a space on which H's live. In the traditional HMM world, that's a discrete space. Okay, but it doesn't have to be. I'll soon talk about places where the H space is continuous. Okay, there is an initial probability distribution of this H, and then there are transition rules. Right, so it's a Markov evolution process of these H's. Once I tell you how H evolves to H prime with what probability. Okay.
So a Markov model always has to have a probability of how it transitions, or what's the fundamental?
Okay. That was fine. So I have then probability of HT plus 1. I called it T because transition T is taken. I'm told these roots. right? So let me give you, okay. So my favorite example in my HM introduction is that you are in some medieval marketplace, and then there is a charlatan there who's giving you odds with a coin, but has an unbiased coin and a biased coin, okay? And he's giving you odds of like 5 bets or something or the other, and nobody knows probability theory. So they're taking bets, and you want to catch them, okay, when he's using the biased coin, but you can only see heads and tails. So he has some random rules by which he moves from one to the other. So these are his transitions between the biased and the unbiased coin. Okay. So if I just know that model, I can simulate what kind of biased, unbiased coin trajectories would happen. And then, as a result of these trajectories, there would be probabilities of seeing heads or tails. Your job is to watch heads or tails and make guesses about whether he's using a biased coin now or an unbiased coin now. Okay. So that's the underlying reality we're trying to get at. So just like this is given, this is the transition probabilities, the emission probabilities, which is what you observe, like heads and tails. Even the hidden state, biased or unbiased coin, is also given to you, right? And then you try to make probabilistic guesses about H. You could do many different things. If you're just going on and at a certain point you say, I've seen so much in past, what do you think the H is? That's like sort of filtering problem. If you look at the whole thing, see the future, you have more information. That's more like a smoothing kind of problem, right? So there are lots of things you can do, okay? Probabilistically, okay. But the key thing I want to, so I was giving this example of a crazy one. It has been used in non-dynamic thing, but for example, when people sequence a genome, you think of going along the genome and seeing the ACGT as if you're seeing something in time. Okay, and then there are hidden Markov models that will tell you, is this region, there's a G, is there some like coding region here? Is this an intron or an exon? So it's very, very useful there. But I will touch upon something else which has something to do with control, okay, which is a linear Gaussian dynamical system, which is kind of fundamental to, for, I don't know, how many of you are physicists? Okay, so physicists have to say, okay, this is the harmonic oscillator of something, okay? So this is the harmonic oscillator of control theory, okay? Where what you have is that you say, oh, the dynamical system essentially is linear. By the way, I should erase it. Yes, for a moment. It doesn't get, okay. No.
I think it'll take care of it at the end of
okay, fine. I should not spend my time cleaning my. Okay. Right. So there is this absolutely linear dynamics. XT, by the way, XT is the common notation. That was my HT. Okay. XT is continuous. Okay. XT plus 1 is A times XT. I mean, actually, if I had a harmonic oscillator and I discretize it, right, then XT would have been the position and the momentum, 2 components of it. And if I take a little time, I can actually predict what would happen to the position and momentum a time step later, right? So that would be my harmonic oscillator there. If it is dissipative, if it is dying, there would be some decay, okay? Right? B times U is basically you're trying to muck with that harmonic oscillator, okay? So U is an effort, like you put additional forces. So again, people's favorite example is that think of a linearized inverted pendulum, okay? This guy is trying to run away from its position 0, okay, if I linearize it. My job is to put additional forces, or torques, which I can do by wiggling at the bottom, right, and trying to keep it straight. So think of like a stick with heavy ball on top of it, and you're trying to balance it. So I apply additional forces. So BU is that term. VT is extra noise, okay? And here comes the observation. YT is some linear function of XT, could be even lower dimensional than, or higher dimensional than XT. And WT is some kind of noise whose covariance is unknown. Now, there is sort of an additional task of minimizing some other objective function, like I want to keep xt squared small, okay? I don't want to spend too much energy doing it, but we're not going to focus on this. Thing we're going to focus on is that if you are given a system and you are trying to play with it, okay, you need to know what these parameters A, B, C, etc. are, okay? Perhaps what the covariance of noise is, okay, if you absolutely must, okay? And also, you have to solve the other problem, okay, which is that I only see YT. Maybe I only see position. I don't do velocity measurements, right? But to dynamically predict something, I need to know both positions and velocities. What can I do? Right. So okay. So that's so part of these two problems. Knowing this problem, I'll call it systems identification. The other one I'll call state estimation. Those are fancy words for figuring out ABC and guessing X from the knowledge of Y and use U applied, so you know. Okay. Okay. So that's what we'll do now. So this is actually like the previous model. It's just that the H, which is X now, is continuous. Okay, and everything is Gaussian. Okay, so okay. So the key thing I want you to remember here, which is not too much math, okay, is that you can iteratively get to know what your distribution of a posterior distribution of HT plus 1 would be, okay, given all the observations. And that's an exercise in just Bayesian algebra, okay? The way you can think about it is that if I saw y1 to y little t, I have some posterior on HT, right? And I update it by saying that by some formula that says, oh, I've seen a new piece of data, okay? If I did not see it, then all I could do is to use my transition matrix to guess what the new probability should be. But knowing the YT changes this balance, okay? And I think so for example, in my charlatan in the market, if he has a run of 10 heads, okay, and he's winning like hell, possibly you know something is wrong. And one more head actually increases your suspicion that he's using the bias curve. Okay? Okay, so that's all. That's the most important thing. Rest of the algebra you can work out. The other comment I want to make is that in the linear quadratic case, again, the U will hang there, but exactly how to choose U is another topic. I'm not going to touch it. Okay? It turns out that in that case, all these posterior distributions are Gaussian. So if I knew something about their means and variances and could figure out how the mean and variance evolves, as opposed to like the full, that's equivalent to knowing how the full distribution evolves. So if I could just summarize, think of the posterior distribution and seeing a new piece of data how the posterior distribution evolves. Okay. And for the linear Gaussian case, it's very, very pretty. You can actually do it by something called Kalman filter, okay? And you don't fully have to absorb it, but it's sort of cool enough that I want you to get a hang of it, okay? So the idea is this, okay? Look at this X hat. So these are Gaussian distributions. So the posterior has a mean position, somewhere it is peaked, okay? And it has some covariance around it, right? And it will be nice to know the evolution equation, okay, from t to t plus 1 of what would happen to the mean and what would happen to the covariance. I'm going to ignore the covariance for the time being, although there are people actually have to do that if they do traditional control theory. Okay, look at the mean. Okay, look at this equation. X hat t plus 1 is ax hat plus bu. Okay, that's the average we expect based on our previous averages knowledge and given the dynamics. Then comes the correction due to new piece of seeing data, right? So if this was exactly YT, I should say I have predicted perfectly I'm taking a vacation, right? But what if your observation, YT plus 1, did not quite turn out to be what you expected in average? It turned out to be a little bit higher or lower in some other direction, right? You need to correct. Remember, we said when we see a bit of data, okay, we should alter our expectation, not just go with what we project, not knowing any extra piece of data. And that correction could be captured. So this ET, this mismatch between observed data and my average prediction. There is some, so this is a vector, okay? And there is some matrix sitting there that tells you how that corrects it, okay? So everything is linear. Everything is a linear combination of X hat, UT, and YT, because it's all Gaussian, right? The new mean is going to be linear combinations of these things, okay? And but this way of saying, when I if I predict things wrong, I correct my thing, is a very, very worthwhile way of formulating this thing, okay? And this would be important in a little bit of the thing I'm going to talk about, okay? Okay, so there is like, this is a whole subject, but I'm just going to spend 3 sentences and move on. Okay, how do you know the equivalence of ABC? Yes, please.
Can I ask you about the previous one?
Previous one, yes.
How do you actually produce?
E at the next iterate, or
Okay,
is the goal to minimize it?
So the way you would do, if I do nicely, I have my X hat T, and I've applied some control UT, like I saw my pendulum, inverted pendulum is here, and I put a push, right? So I can calculate according to my model, if I knew A and B, where on the average I want it to land. That is X hat T, this thing, and BUT. What is my average observation for that? Okay, C times that, right? For example, if this combination had both the position and the momentum as top and bottom component of a vector, I'm just watching the top. Say I'm only observing position, right? Okay, but where is the position now? I look, I see it is away from there. So I take the difference. This is sort of the innovation. This is the part that I'm surprised by. I'm going to call it the surprise variable. Okay? My experiment says my theory may be wrong. Okay? And I say, oh, it is too much to the left. Let me go correct my new xt plus 1. Okay? Right.
Okay.
So theoretically, I said it was going to go there. I see it's there. I said, now I really need to work because I think it's too far off. Okay, maybe need even bigger force to bring it back. Okay. Okay, so turns out that LTs are functions of all these ABs and other parameters, but it's a pain if you don't know them, right? To learn these parameters, okay, there is something called expectation maximization. I'm not going to get into it. You most probably heard of it. Please read up. Of course, you can take log likelihood and just do gradient descent. Okay, in parameters, everything is done by gradients these days, so not a bad thing. If you are super Bayesian, you can set up some priors on these things and do MCMC. There are all kinds of ways of going over this parameter space. It's not as bad as it looks. Okay, so okay. Now, so one way is to really learn ABC and the covariances and compute this L parameter. Now, turns out that if I have a more or less stationary system, right, my things have kind of settled down, this L becomes kind of independent of T, right? And we can do something crazy. We can say, hey, I'm going to find this ABL parameters by doing this following. I don't want to have not too much surprise. I say norm of E squared, right? Sum should be minimized by mucking with AB, right? This is an approximate way of going about it, but it actually does operate pretty well. Okay, so there I'd say I did not know any control theory. I'm just going to train my networks or train my various functions in this thing in a way so that this surprise strength is minimized. Yes.
Why is L independent of time?
Okay, so this one I would take off. So what happens is that I could actually start with the inverted harmonic oscillator, which is a very unstable system, nothing stationary about it. But if I put an appropriate feedback on it, the system would be stabilized.
So yeah, it's like after a long time.
After a little bit of time, things would settle down to some routine, and the optimal L would actually settle down to something. Optimal L is function of all kinds of things, including covariances and other things, and covariances of some noise and covariance of this estimate. They all kind of converge to something. If the environment changes, you have to change and start again, right? Okay. Okay. So I'm actually now going to jump over this. So we applied, part of this was useful in thinking about some problem. There you see Siavash. Okay, about something about sensory motor system in the brain, right? And well, as you can imagine, people moving around playing tennis, for example, okay, is trying to learn about the world. And in some sense, you cannot quite play tennis this way. I just swing the racket, okay, and if I hit, okay, and the ball goes and get a point, only then I respond, right? It will take a long time if you just blindly try out all kinds of shots and see what happens, right? When you see the ball coming at you, I don't know how many of you are tennis sports, right? If you haven't already have a mental picture of its trajectory, right? You most probably can't play because with the latencies, okay, you need to know where it is, way before it is there, right? So when we become better at it or figure out a particular environment, I'm sure the top players figured out that, okay, today court is hot and things are moving faster, and right? And another day it's different. That little adjustments actually come from building an internal model. And most of us would not be anywhere because the data that comes to us comes late, comes with noise, comes poorly, okay? So anyway, in sensory motor control, presumably building an internal model is important. And what we wanted to do there is, rather than just have a normative description or just starting to talk about brain, talk about how we can have learning in which we can kind of say, okay, brain could learn this because synaptic plasticity rules of brain require information from the neighborhood. And okay, so I would actually almost skip over the rest and say, we could do it, okay, right? So this half of the top of the picture is about control, but that half is about Kalman filtering and way of learning, even for this linear problem, learning Kalman filtering in a biologically plausible network, okay? So maybe it has some use. We can say, oh, look, here is a system with delays in which if the delay increases, it takes longer time to learn, but it still learns, right? And we can also mimic some of the strange experiments that people do where they say, oh, try to move hold this device, move it here. And then they suddenly turn on a crazy feed, effectively, where if you try to go this, you get pushed sideways, okay? And pathetic people then start, like, instead of making straight rope for it, make this very bent out things. But with time, okay, they learn to compensate for it, okay? And well, in human experiments, things kind of improve over time, right? They figure out those routes, okay? And okay, well, if our network did not do it, we will not quite publish this paper, right? But okay. Anyway, so here is the first breakpoint, and I have eaten up like, yeah, quite a bit of time. So is there a question that about the first part? And again, I'm not obliged to finish according to. Okay, but of course you could say that now you can go, but okay, but that's most probably not in the books. Yeah.
Can you explain, like, what do you mean by biologically inspired?
Okay, so the thing is that if you just take some objective function like likelihood and you say, oh, take a gradient with respect to this parameter, and I would say these parameters would change like this, right? So what would happen is that, of course, who are these parameters in our brain? Presumably synaptic strengths. Now imagine you say the synaptic strength improves by this neuron whose synapsicity is its activity, and 13 other neurons which are very far away, who are not talking to this. That doesn't seem like Hebbian or any kind of even non-Hebbian biological rule. So all the machine learning gradient rules you get, not all of them are easily implementable in terms of what we understand about synaptic plasticity today. Now, this is a bit of a dangerous game because biology, you often say this biology cannot do, and you find then some crazy way biology does that just to spite you, okay? But if we say today we understand how the brain does plasticity, okay, how synaptic plasticity happens. If I want to make it consistent, you need some tweaking. So that's what one is trying to do. One trying to find rules for learning the dynamics, etc., where we don't have to make unreasonable rules about synaptic updates. So this one actually satisfies more or less reasonable rules. Okay, so fine. Part 2. Okay, part 2. Okay, so as I said, I will try to make however tenuous possible efforts of connecting things. There are many discussions of neural net-based ways of looking at dynamics, where you can start from scratch, say neural nets, and just move. But I'll sort of try to make some connection to what I said in the past. And hopefully, if you hear of parallel methods or something, you can kind of try to say, oh, A should correspond to B. Okay? Fine. So I'll talk about recurrent neural networks. I'll talk about a particular kind of thing which is kind of like the recurrent neural network, a very special one called neural ODE. Okay? That's because we did something with it. Okay? And we'll talk about an application to quantum many-body theory. That's something that Domenico was working on. Was nice enough to call me. Okay, so I am not going to spend much time on this, but you have heard enough about feed-forward neural networks. The way to broadly we just need it here is to say people think of them as some sort of universal function approximators. Okay, I'm not too fond of that. But let's say, yes, anytime there's a function to be approximated, why not try a neural network? And then the function is characterized, okay, by the weights in this humongous mess, okay? And as you know, these days, the neural networks have more parameters than most probably data points, right? People used to be afraid of it in ancient times. They now no longer are. There is some degree of justification given why we shouldn't be afraid, but not a clean one yet. Okay, but that's the status. Okay, if you could train a neural net to approximate a function, we can maybe go. Okay, so remember I said that in Kalman filter or something, we are thinking of a Gaussian distribution evolving. Okay, and then there was a mean, and then there was a covariance, and I said I'll forget the covariance. Okay. Now, you cannot really forget the covariance there, but I kind of found a work around it because I could use the L directly learn it from data. But what if we could be like that? What if we say, we are going to be crazy and make this approximation that this posterior distribution is all concentrated at one point? Okay, well, then it is nothing other than a deterministic function, right? That is, you tell me the past yt, okay, and the past ht and the new data piece, and I'll be able to tell you what, actually maybe I should have said yt plus 1, okay, but you get the idea. I know the past state, okay, deterministically rather than a probability distribution. So could be the mean, could be the mode, could be something. And I give me a new piece of data, I'll tell you what the new guy is. Okay, so So this is often drawn. YT and HT together determine what the new HT plus 1 is. Okay. These arrows, by the way, these are the arrows in which the neural network is working. Previously, the arrows went the other way, right? From HT to YT, right? Those are the diagram of the generative model. Okay. So here it will get reversed a bit and go to the wrong guy. Okay. But this is how we'll think about it, right? So so there is a dynamical rule. The dynamical rule is affected by YT. HT is like some secret latent space, again, right? Which captures all the information about the past. So that going forward, we don't need, okay, to know all the Y before that. Okay. And by the way, this is a tension that has not completely gone away. I started out in the probabilistic part saying, oh, I have the whole train of Ys, right? And tell me something about the future. And in theory, all of past could affect, right? Then I could say, no, only past beyond K affects you. And then I said, no, it's even better to say there is some secret rather than put an artificial time limit. I capture it in terms of some, either call it hidden state, call latent variables in terms of it. All of past is captured in terms of the knowledge of a probability distribution of those HTs. Okay, right? So it turns out that RNNs, neural networks are taking that point of view. Okay, all of past is summarized in the current HT, right? And there would be other set of approaches, right? Especially the current day favorite of attention or based sort of transformer networks, which says, no, give me the whole input thing. I will figure out what's relevant. And in language models, this is actually an issue because, as you know, if I want to translate some piece of language, something very early, a context saying this is happening in a courtroom, okay, most probably changes meanings of lots of things. And you need ways to remember that. And you can do it either by having some degrees of freedom in your latent space that remembers things for long, or you have to have some way of saying that if I see this kind of thing now, word now, maybe I should go check, okay, 20 words behind, whether something was said that said it was in a riverbank or a financial institution, okay, right? Okay, so that issue, but okay, we are taking the RNN look. Well, it's recurrent because it looks like the neural net has neurons that are interacting with each other. Feed-forward networks kind of don't do that. Okay, so there are models where I have this YTs coming and some O bar T's go out, which are sort of predictions for observations. So for example, I could have a sentence running in the language context, and I could say, okay, what's the current sentiment or topic? Okay, or if you are really, really brave, you could say this is an English sentence, sort of throw out the French translation of it. Okay, that usually dies in the simplest thing. Okay, you have to do more. Right? And then you can check with some training data of what the observations are and see whether the O-bars predicted a LIGO. Right? So that's what would happen, sort of a sequence to sequence RNN, right? Those would depend upon the secret variables, right? And we can actually consider a special case where I'm really predicting future Ys that are coming, right? And I can just see whether these Ys are produced correctly, right? That's a simpler case. I want to just self-predict, right? Based on past, okay? Right, so as I already commented on it, you will hear things about things with GRUs, LSTMs, etc. These are vanilla RNN forgets things from the past, okay, because it has limited space to remember it in its age variable, right? So they kind of work very hard to make special components that remember a lot, right? But you could also use some other approach, like attention mechanisms, which figure out whether we should go back and look at something else. Okay, but this is something where maybe other people know a lot more than that, and I'm basically trying to avoid talking about it. Okay, so here I come to something that is closer to this stuff. Lot of things in in physics, right, are essentially differential equations, right? A lot of, not quite physics, even outside physics, right? Dynamical models, like we have both ordinary or partial differential equations. You can think of partial differential equations as ordinary differential equation in functions, right? So again, I have some. Now, quite often, what I might want to do is to ask, is there an approximation to this dynamics or a way of describing this dynamics in terms of some simpler variables? Okay. So I've tried to do the same thing here in a continuous version, right? I have y's, which I observe. I want to convert it in by some encoder function to, oh, by the way, one of the things I wanted to say there is that these f's and g's, right, which are functions I have to learn, you can use the parameterization of feed-forward networks, the multi-layer perceptrons, okay, and then train the w's to look at the loss, okay. So here also, I have these three functions. One is what that converts my observed y's into some hidden variables, okay. The second function that tells you how the hidden variable evolves in under a differential equation. So h dot is some function of k. And y bar t is the decoder that says, given the hidden variable, what do I think the y variable is? So I have these three unknown functions from high dimensional space to reasonably high, maybe lower dimensional space, but not quite scalars, okay? And then we can say, oh, I know from some either observing dynamics or from some simulation, yt is what I see, right? And y bar t is what I predict. I have some loss function, maybe this minus that square. I might say I want to see over the whole path, it is low. I might say I want to see at the end, it is low. So I can weigh differently, different types, okay? And based on that, I could say, well, can I find the best ek and d? And once more, ek and d could be parameterized as this sort of feed-forward neural network. And you can train its parameters, okay, to find the one that will minimize the loss, okay? So, okay, yeah.
So as you wrote here, the encoder is only on the initial conditions? Or
You actually can see, you can, if you have the encoder, you can also use it halfway through, because I still know y, right? And you can sort of convert it into the corresponding h and run and predict. Now, so think of the zero shifted.
Oh.
Right. So yeah, the thing we did is closer to doing it at the beginning, and also we did a TT version of it. But yeah, in principle, it should work everywhere.
Like, yeah, it should be able to.
Right. So exactly how do you set up the loss function? You could actually have different starting and finish points. And also you have to have some kind of weight for different amount of prediction, right? How do you value that? Right, yeah. Yeah, definitely a worthwhile modification. Okay. So the application of this, I'm going to do to something quite weird and maybe even takes up too much time to explain. Okay. So the application we're thinking about is not, okay, traditional dynamics, but something called renormalization group. Okay. And what is renormalization group? It's this idea that if we go to different scales, right, we have different effective Hamiltonians or different effective dynamical rules. So I again keep on going back to my example of describing particles bumping into each other to overall diffusion of intensity, okay, or of momentum, right? We have this coarse-grained long-range descriptions, right? And the point is that as we go from small distances to large distances, we can rescale it and try to make it look the same, right? But as we do that, our dynamical rules change. Okay, so there is basically a whole new set of dynamical rules or Hamiltonians, etc., that has to be written down at each level, and they're related to the previous levels. previous scales dynamical rules. So this is actually made successful only in very particular setting, but this was a revolutionizing thing, as many of you know, in 70s and 80s. That has kind of changed how particle theorists and condensed matter theorists at least look at the world. Okay, and these are some of the heroes of that development. Ken Wilson is the one who got Nobel Prize. I guess most of them are gone now. Michael Fisher passed away a short while ago. Anyway, but the interesting thing is that what especially is Ken Wilson's contribution here is that you should think of an infinite dimensional space of Hamiltonians. Okay? Many, many dimensions there are actually not going to matter. Right? Many details are not going to matter, but a few details are going to be important as you go to the long distance thing. Right? So again, I could have many different rules for the potential among the balls that are bouncing with each other. But overall density profile will be determined by one thing, that is the effective diffusion constant. Right? So at the end, what matters are very few things out of this huge number of parameters. Okay? That seems like what we are talking about, except in scale space rather than in time. Okay? So here was an example that is a project in CCQ. So here you can see Domenico. Okay, and this has to do with something called Hubbard model. Okay, so which is a model for interacting electrons. In this case, the Fermi surface, in this case, a Fermi curve maybe, okay, is like this, not very, very round looking, right? And there are points around it, which is a momentum at which electrons or holes can be found. Okay, and there is a scattering strength. If electrons come with K1, K2, when they scatter out to K3, K4, what's the amplitude of that? Okay, and it's a function. If we have momentum conservation, it's a function of K1, K2, K3. Okay, and as if you discretize points around K, here what is 48 points, right? Right. Essentially, it's a function of 3 variables, each have 48 values. So superficially, there are 48 cube numbers. With symmetry, is a little less maybe, but it's still a huge number of variables. So it is looking very much like the previous picture, very high dimensional characterization of Hamiltonian. But the point is that as we coarse grain it, okay, as we go to longer and longer scales and try to see what the effective interaction is this something that's going to become lower dimensional in some sense? Okay, and how can I figure it out? Now, most of the time physicists say intuitively, I think this is the most important channel. Write down a 1 parameter thingy and we get there, right? Now, this model turns out to have a reasonably rich physics, and it does different things at different times. Okay, now I have a bit of an issue here. Okay. So, right. So the point is that as there's a parameter called T prime, at that cranked up, it goes through different types of behavior. Yes.
Sorry, I didn't get what K1, K2, etc. are.
Right. So basically, these are fermions, right? So I start out by quantizing in a box the wave-like function. So there are single particle states which are like e to the ikx. K's go over some grid. Okay, if I keep the box finite, right? These are all single particle states. Now, if I had no interactions, I'll fill up the Fermi sea, right, up to some threshold. Okay, and essentially at low temperatures, I'll have electrons go to energies close to that Fermi energy from below to above. So I get holes and particles, okay, close to that. Now I make this thing interacting. And now I can say, if from this Fermi sea, I wake up 2 electrons, a little bit with higher energy, and then say, go at each other. And I say, there is a Hubbard interaction between them. Okay, there's a 4 fermion term now. with two fermions going scattering against each other. And you say, what is that function like? In the raw Hamiltonian, that looks like a constant because it's like a delta function. Okay. But you say, oh, if I coarse grain some and look at K's, what does it look like? It keeps on changing. And it changes to very different things in different ranges of parameters. Suggesting in some cases, maybe there's an antiferromagnet, in some cases, maybe there's superconductivity developing, some other cases, ferromagnetic. Okay? And these various pictures are slices from those different types of behavior that arises by coarse graining. Okay? Roughly the same vertex. Okay? With some parameters being different. Okay? In the other parts. Right? And here we have the network pretty much like what I suggested. Except one cheaty thing is that since in the beginning life is simple, right? We have an encoder from a pretty low dimensional space. But that Z can be run through a differential equation we learn, and we can spit out what the V's would be. And we can do the painful work of numerically coarse graining and figuring out what the V is, and we train on that data. And the network we create can reproduce, okay, this complicated vertex function, okay, and without having seen it before as part of training. Okay. Anyway, so we are 25 minutes away from end. Okay. So there's the third part. Well, but I'm sure I've said enough things that are confusing. So are there some questions? Yeah.
For the neural you mentioned earlier,
Yeah.
how do you find, like you had a K
Right.
or a K neural network, but
Yeah.
how do you describe the dynamics? Is it just the K, or you were?
So the dynamics is determined by K, but K also, as you can imagine, is a function parameterized by lots of weights and a neural network. So those W's have to be updated to learn that appropriately, as we have to do for the E and the G. So all three of these functions are being trained at the same time. Yeah.
Where does like the work?
Okay. So in the picture or in the I most probably went too fast on it. Okay. So see here. So if in general you're asking, or in this particular context?
In general.
In general. So, okay, I'll even give you the particular context even if you did not ask for it. Okay. So the Y, right? It's like my vertex function. In principle, okay, 48 cubed, which is more than, I guess, 100,000, 124. I can't do this. Okay, very large number of things, but it might have started as all constant. Okay, there is some encoding that will make it into, say, an H, which is, say, 32 dimensional. I've chosen 32. We've tried many other dimensions. I was showing you results with 32. Okay, then I try to train a network that says these 32 variables, how do they evolve in time? And then there is another function that says, given this 32 variable, I'll produce for you, okay, the, I don't know, 48 cube numbers. Okay, so that's how the thing goes. Okay, and basically you can kind of see the reason we are succeeding is that these 48 cube numbers are not crazy. They have structure. They have a general background. There are places they are bright. There is actually a lower dimensional structure to learn. And the lower dimensional structure is different in different regimes. So the neural network has to be clever enough to pick up, okay, what to do differently at different places. Okay. And it just that it somehow manages, right? Okay. Any other questions?
I think related to
Yeah.
the question in your answer. So if I understand correctly, the assumption is that the overlying dynamics are actually dominated by dynamics on some lower.
Some latent variables on lower dimensional space. Yes.
So is there like a smart way to choose the encoding space, like how big the
You want to tell me you know, honestly? Yeah, no.
No, I'm asking.
No. In this game, basically, you try A, try B, try C.
Also, just like crossroads.
Okay. Right. So one of the great things about neural nets is that it is let us be dumb. Okay, which is actually not let us be dumb. It's sort of some poor person who is doing this. Okay. Usually, the professor declares victory, and there are several graduate students and several others who have succeeded, right, in finding the right hyperparameters. Okay, who sort of said, okay, now it works, and everybody is sort of. Right, so it's a sad state of affair. I wish there was something more intelligent, but as far as I know, no. But you have to be, of course, careful that in that process of searching, okay, have you actually fit both your test and train data set, train and test data set well enough and declared victory? Because I think we're coming to a point where you are risking that, right? If you search high in sort of large enough architecture space, you will find something that leads to success. Yeah, so it's a bit dangerous. So you have to sort of, so one of the things I'm not talking about is that we spend a lot of time afterwards asking how did it succeed? Because we don't kind of believe that it should succeed that easily. So what we found is that actually there were neurons which are roughly tracking what kind of phases. There are a collection of neurons who together was sort of coding what kind of phase the system is in. And having that regularity, which I'm not showing, that some partial interpretability made us feel a little bit more comfortable that this is maybe okay, right? In theory, then, you could have said 3 variables are good enough, okay, right? But it turns out that sometimes the network finds a solution if you keep it a bit higher dimensional because it has a little bit more room to do that. I'm just, now here I'm in the blah blah territory. Okay, if you really make it 3-dimensional, it will do a most probably crappier job. We know that, like the dimension, you can push it to 8, you get a little bit worse performance, but it still does something.
So this has more to do with the optimization.
Yeah. Whether the optimum would be found, even if like 3 to 4 or 5 dimension is good enough, neural networks parameterization most probably is not easy in that, yeah. So it's not just the true dimensionality of this space. Okay, fine. Any other question? So I would, the last one, I know it's most probably exhausting for you guys, right? Okay, we have entered this sort of death contract that it will be till 1:30, so I'll make you suffer a little bit more. Okay, so let me try to sweeten it by saying this thing is a little bit about the dimensionality question, as if it will please you, right? Neural nets are a bad way of getting to really how many dimensional is it. Is there a compression? Yes. Okay, exactly how much compression? Maybe we can try to figure it out, right? But yeah, okay. So this is what was the last part of my thing, called something called dynamic mode decomposition. And it's based on a certain number of hopes that almost look like against each other first. Okay, one of the hopes is that despite the fact that that lot of dynamics we have to deal with is nonlinear, maybe if you go to very high dimensional spaces, things would become linear, right? So the way people would try to tell you that this is possible is that imagine I have some differential equation like say dx dt is x plus x squared. And you say, hey, I can make it linear. Okay? You say, well, it's not a linear differential equation. I can see it. I say, no, it's a linear differential equation. If I call this one x1 and call this x2, I have dx1 dt is x1 plus x2. Looks linear. You say, no, you have to tell me how x2 evolves. Okay? Well, so now I start writing x squared's derivative Okay, sorry, this is a very bad idea. One. Okay, so you see this is x dx dt. Then you write it out. Well, dx dt was x plus x squared, so it is x squared plus x cubed. Okay, so then I need an x3, which is x cubed. Then I can write dx2 dt is x2 plus x3. So essentially, I'm cheating. Every time there is a nonlinear term, I'm calling it a new variable, and I'm finding it a rule. Now, how many dimensional vector space on which things would be linear at the end of the day? When would I stop?
Infinite number.
I'll have an infinite dimensional vector. But if I made it infinite dimensional, voila. Okay, so the price you paid for doing linear things is that you got an infinite dimensional linear problem. We said we are much old people. We did quantum mechanics, infinite dimensional linear thing is nothing for us. Okay, but fine. So that is sort of the idea. But actually, this idea looks like, okay, this is somebody's parlor trick. Okay, it's never going to come out of, nothing is going to come out of it. Okay, but if you go to some other parts of machine learning, people are selling you, or rather, what was popular before neural nets again took over the world, were kernel methods. And the idea in kernel methods is the same, right? I have to do a classification in some lower dimensional space. I have to separate cats and dogs. The boundary is very, very wiggly between the cats and dog pictures, right? The reds and blues. But if I'm lucky, and if I could have a whole function expansion and take an infinite dimensional space, well, the decision function could be a linear combination of this expanded basis, right? So in some infinite dimensional space, it's a linear separation problem, right? So this idea that, hey, perhaps there is some sort of infinite dimensional feature where just a dot product with W gives you the decision function. If it is positive cat, negative dog, okay, right? And also those guys tell you that in most cases, all you need to know is how dot product works in that space. And everything can be captured, the decision function can be written as a linear combination of some kernel function, where one leg of the kernel would be your sample space, okay? And other leg would roam free, okay? So this infinite dimensional expansion plus kernel tricks is something that was like in mid-90s, late 90s on. This was the method. Everybody was convinced neural networks are never going to work, okay? Even in early 2000s, okay? So this is not such a crazy idea. Maybe let's see whether we can do this infinite dimensional thing. But see, this linear description of a nonlinear system is therefore trying to say, I'll go to very high dimensional spaces. Or if your data is already very high dimensional, maybe it's good, right? So it doesn't say immediately, I want low dimensional spaces. But what this method essentially is also saying is that the linear dynamics I'll get in that space. So remember, I had this infinite dimensional dynamics with some A matrix now evolving it forward. I'm hoping that the simplicity of the system is that matrix, this infinite dimensional matrix being effectively low rank. What that means is that if I could take this infinite dimensional matrix and diagonalize it, again, we make a living of it, right? Most of its eigenvalues may be complex, their modulus is small. Okay, and only few of them have either growing things or more or less marginal things or something that decays slowly, right? So it says expand the dimension, but please, please, please pray that there is a low rank dynamics in these infinite dimensions. Okay, now,
Sorry.
yeah.
Is, just to understand correctly, is that equivalent to finding a basis in which the model is linear, or?
It is equivalent to finding a base. Okay, so the truth is that kernel people, okay, anytime they give you a kernel, they have essentially given you a basis. Okay, there is this sort of Mercer representation which will just take the kernel and factorize it in terms of its eigenfunctions, especially when it's a compact operator. Okay, so it has a basis associated with it, right? So with kernels, okay, what you are praying is that the basis the grades have given you is useful for the problem. The neural net folks would come and tell you, we are a bit more flexible. We can approximate all kinds of functions, and you don't have to start out by knowing a kernel and a particular kind of basis that's good for this problem. Okay, right? And it turns out that if you take traditional feed-forward networks and take their very wide limits, they actually turn into essentially kernel methods. So neural networks in the very wide limit are particular kind of kernels, right? But finite with neural networks, in some sense, a little bit more flexible than. So again, if you found the right kernel for your problem, okay, please be happy, right? But there's no guarantee it is. So people also try the same thing, nothing intelligent. Kernel 1, kernel 2, kernel 3, see whether you succeed. And if you cry, then okay, you finally have to do it. Okay, anyway, so in the last 10 minutes, how much suffering should I put on you? Not too much. Okay, so okay, let me just give you the broad picture, okay, and call it a day because it's been long and I'm sure I'm exhausted, you must be more exhausted. Okay, so we have solved all sorts of ghastly equations, right? What we have, as we said, generally it could be nonlinear, but we want something, I want to know whether there's some change variable where it's linear. Some cases with high dimensional things, we might say, does it look like linear to you? Okay, and the reason this subject got started, something this crazy, is actually some observations that in an odd way, things that should be nonlinear, you can find like things like eigenmodes there, okay, in terms of which you can describe the system pretty well. So this is some crazy example where there's somebody who observes fluid flow, has a little metal sheet, a little rubber thingy that is fluctuating, fluid is going past, eddy is getting shed left or right. Anyway, meaning fluid dynamics has gone out of at least American graduate things. I don't even understand anything, right? But when you take those, the flow pattern they observe, and you say, can I expand it in terms of a few modes and predict how this will evolve, and which modes are dying fast, which modes are dying slow, there seems to be all these modes with certain eigenvalues associated with it. If you pretend it's a linear system and try to fit, you do a pretty good job. And the question is, how come? Right? So in the next 10 minutes, I'm not trying to explain how come. Okay? But I'm just trying to tell you that there is a whole world out there, okay, where essentially you can do the following thing, okay, operationally, okay. Imagine you've got this XSR, think of this fluid flow picture. I saw the fluid flow picture now, it's many, many pixels, it's a big X, very long, tall vector. I see a second later what happened. That's my Y1. And then I start from another thing, I watch it. Of course, I could be lazy and I can have one whole video and I say, Y1 is actually X2, okay? And Y2 is really X3, right? That's the cheaty way, right? It'll be better for you if you can start from more than one different initial conditions. You get a richer set of things, right? So I basically gave you a cloud of starting point and a set of points where it ends up. And if it is high dimensional, we can go say, oh, can I find an A that makes Y into X? Okay, that's actually a regression problem. If I could invert X, then life would be good, right? It would be just Y X inverse would be your best estimate. Okay? Life is not good because quite often, okay, X is a very, very tall vector and I have only so many samples of it. So this matrix is like a very sort of like a Manhattan building. Okay, but you could actually do something called pseudo inverse there using kind of SVD, right? And you can make an estimate of it, right? And you can look for its eigenvalues, right? And turns out that now if you give me a new X, if I know what the eigenvalues of A's are, I can do an expansion of X. Now, it turns out A is not, okay, a nice matrix. It's not normal. Its left eigenvectors have nothing to do with right eigenvectors. But if you know the left and right eigenvectors, you can figure out how to express A in terms of this coefficient B alpha, which are taken by dot product with left eigenvectors. And then there is right eigenvectors, which look like your original image. They are long and tall, okay? They are the modes, okay? And you can say, I keep only first two modes. How good is the prediction, right? Now, the next two pages are about how you can do it completely in the sample space in very kernel style, okay? At this stage of exhaustion, I'm not going to torture you, right? But you can actually go beyond this sort of dot product linear, what's called linear kernel, and use more complicated things. There are equivalent formulae for it. But let me come back to these pictures that we started out with. You can say, oh, you have this fancy neural network predicting things. Can I get my little linear model predict things in this high dimensional space? And lo and behold, okay, if you keep like, you can see 1 mode, 2 mode, 3 modes, 4 modes, 5 modes, and you're sort of predicting the final things, right? You do pretty well, okay, even with 8 modes. Meaning the vertical direction is a log scale, and things have fallen from 10 to the 2 to, I don't know, 10 to the minus 3, something, quite a bit, right? So it is possible to find structures by this oddball method, okay? I mean, there are days, Domenico and I would say, this is working, but this can't be working, right? Okay, so there is some mystery out there, okay? And the fact that the neural net succeeded is because there is some kind of structure, that this method is getting to some sort of effective lower dimensional dynamics is very likely the same thing, the same reason. Anyway, so I think I have spent enough of your time, and okay, yeah, please.
So this method that you talked about, DMD,
Yeah.
there's no neural network there.
You doesn't give up?
There's no neural network there.
It's not a neural network, right?
It's
At this
some-
point.
Okay, so it's just some sort of like.
So it's kind of like the closest thing of that is actually like a kernel method that is suited to dynamics. Okay, it's trying to find a way of finding modes which are simple under dynamics by some kind of kernel approximation. Now, there are people, of course, again, if there are functions to be learned, somebody would stick in a neural net, and there are versions of this where you might try to do something more neural net-like, right? But in some sense, the attraction of this is that it's not hidden in some neural network mumbo jumbo. If you find such mode, you can ask, for example, interpretability-wise, a straightforward linear algebra method may be better than a neural net that actually performs well, but doesn't give you much idea about, why and how did it succeed, or how many effective degrees of freedom do you have.
So is it possible to like take a neural OD and do DMD on that to maybe get like more interpretability?
Yeah, okay, so we didn't quite do that, but we trained on the same data. So my suspicion is that if we actually now DMD the neural OD that we learned, which is not quite the real data, but close, we'll most probably get something similar, but it's a good question. Okay. Any other questions?
Well,
yeah.
Generally, the actual practicality is just like doing something similar to kernel PCA.
This one?
Yeah, but like the DMD, is it like using kernel PCA?
It is somewhat, so there is a thing here. So when you have this access, one of the pre-processing steps of DMD is trying to do something like a PCA, because the X could be quite noisy. So you first try to reduce that dimension.
So it's not the operation itself is PCA, it's just like pre-processing.
No. But what I'm trying to say is that you can do something like kernel PCA there to sort of denoise the original X. But so think of it this way. Okay, this makes no mathematical sense, but formally, this is what's happening. I have these X data points, vector. I have the Y data points, which is like what happens to these initial conditions after a short while. In general, okay, if I said it was scalars, you will say just fit Y over X. So I want to do YX inverse with rectangular matrices. That's what I want to do, right? The DMD question is asking, when I do YX inverse and X has lots of zero eigenvalues, how many modes do I want to have? How many non-trivial eigenvalues of YX inverse do I, what rank approximation do I want to do to YX inverse? PCA is much more about what rank approximation, low rank approximation do I want to do to X itself or Y itself? And this is what is the low rank approximation to what should be morally YX inverse. Does it make sense? Yes. So this is a kernelized version of that. This is trying to find out what the dynamical rule is, because that thing is supposed to estimate what your dynamical rule is. Okay? Okay, I think we all can take a break.
Let's thank you. A few practical announcements today. So first of all, just a reminder, while we're here, the building's asked us to not bring any food or drinks down from the 17th floor. So please eat all your food, drink your coffee up there, or get the coffee here. So for today, what we're gonna do, you don't have to.
Okay, I am disconnected.
You can disconnect
Yes.
if you want.
Yes.
All right, so for the rest of today, we're gonna go over to the Flatiron now. The next talk is at 11:30, so we have an extra long break. We can get coffee there, snacks, whatever. And then we're gonna do lunch over there also on the 11th floor. There will be box lunches for the whole Flatiron staff. And then you have some free time until Jan Lepen's talk at 3:30. And you can just stay, there's plenty of space at the Flatiron, or you can do whatever you want until then. Tomorrow, you may or may not have noticed the schedule has changed in the morning talk. We had been moved to next week. So the first talk tomorrow is not until 11 a.m. And it's over at the Flatiron in the 7th floor classroom we were in yesterday. So you can get breakfast at Flatiron if you want on the 11th floor. They have oatmeal, fruit, yogurt, but it's only till 10 a.m. So you have to get there before 10 on the 11th floor if you want that, or get breakfast. But show up at 11 on the 7th floor at 162. And then for lunch after that talk, you can either order seamless and then it'll be, at 162, or our afternoon talk is here, so you can come back here and I'll either lunch if you want. Totally up to you. Just make sure your seamless account is up and running. It's Friday. There won't be any catered lunch, so if you want to eat, you got to be able to order it.
Sure. Would be introduced a newcomer. Would you like to say 2 words? So we did go around on Monday and everyone, but since you just arrived today, I think very much you can introduce yourself, speak who you are, what you like to do, science-wise or ML-wise, and then fun facts. What else did I miss something? Yeah. Okay. Hi everyone, I'm Lindsay Clark. I was traveling last day, so I missed, but tried to join virtually when I could. I'm from Rutgers University in New Jersey, so kind of local, commuting back and forth. And I study supernovae. I'm particularly interested in modeling their spectra. And I'm pretty new to machine learning, so I'm excited to
I guess I also never introduced myself. I'm Natalie. I'm on the organizing committee here. I'm a postdoc at the Flatiron. I work in the Center for Computational Biology, and I apply all kinds of algorithms, machine learning, and not to genomic data. After one side, this is Monday.
I have a 1.5-year-old daughter who's really fun. And I'll keep them in for to make sure I can see her.
My fun fact is that I'm a rock climb.
Ooh. One more announcement. If you cannot keep your mask about your mouth and your nose, you can go on Zoom. This is very serious because there's a lot of people getting COVID in the city and inside of my institute. So we cannot do that. We have a Zoom. So that's basically how it works. And I hope that people will do that, especially in all the paper rooms and smaller rooms. We're gonna have people sitting next to you the whole time. So you'll find everyone wearing a mask, especially in these rooms and the small ones. Thank you so much, and I hope you enjoyed the talk today. And thank you, Oliver.
Well, thank you for inviting me. It was fun.
All right. Hey, everyone. Oh, is this okay? I'm very excited to announce Barbara Engelhardt in her talk. She has been at Princeton until about 2 months from now, and she's moving to the Gladstone Institutes in Stanford. Barbara does really, really amazing and exciting work in various ML and statistical ML applications to genomics and biological data. But she's going to talk today mostly about, I think, more methods, not less genomics, is my understanding, unfortunately for me, but we'll get a really great talk on dimension reduction. So unfortunately, Barbara couldn't join us, but I think she is available for questions via email, hopefully afterwards. And obviously, please feel free to still ask questions. If we have ceiling mics, but in case she can't hear, there are also these mics on the table that you just press the button and then speak into it, and she'll be able to hear your questions much more clearly. So feel free to ask, and please go ahead, Barbara. Thank you so much for joining us.
Thanks. Thanks to everyone for being here. I am so sorry I'm remote. Yeah, it's end of the school year. I'm a single mom, so I have a lot of stuff going on. Yeah, I'm really excited to speak to you, though. I have to say this is something I've been looking forward to for a long time, and life throws curveballs at you. So today I'm mostly talking about dimension reduction. The first half, I think, is going to be more of a tutorial. And I'll say I'm writing right now a review article for a genomics journal on dimension reduction generally. So this is kind of the unorganized version of that. I just want to sort of give you a set of tools for dimension reduction and think about why we do dimension reduction and how to do it properly. The second half, I'm going to talk to you about 2 examples from my group where we've done different types of structured dimension reduction that hopefully are going to be informative. So dimension reduction is called a lot of things. If you were Tukey in 1977, you'd call it exploratory data analysis. In machine learning, we call it unsupervised learning. So it goes by many names. So the really high level idea is that you have a set of samples, which in this matrix for us, thinking about biomedical data, is going to be on the columns, actually. It's usually transposed, but I'll explain why. And then you have a set of features, and those features are on the rows. And you notice that if you think about each of these samples, right, on the columns, they're going to live in some very high dimensional space, right? It could be the space of gene expression of 20,000 genes in the human genome. So each of these points, again, exists someplace in a 20,000 dimensional space. And the idea behind dimension reduction, broadly writ, is to basically project each of these points in this 20,000 dimensional space down to some small number of dimensions, k, where k is much, much smaller than the original dimension of the features p. So here is just a projection down to hypothetically 2 different 2 dimensions. And I'm going to explain exactly what this plot is in a few slides. Why do we do this? So I know you've probably read some papers in genomics recently. It is literally the first plot of every paper right now is some sort of t-SNE visualization of single cell data or genomics data, however it is. It's pretty much the first thing you do. When I have a new data set after I clean the data, it is also the first thing that I do is run PCA or some version. What's up? Very good. Okay, run PCA or some version of that and visualize the data. So why do we do this? We do this basically for the purpose of discovery. So what we're discovering is patterns and trends among a set of samples and among a set of features. The idea is to develop some kind of data-driven hypothesis, if I'm thinking about it in the biomedical context, which we're then going to take and test out of sample. In fact, these hypotheses can be used to design experiments that we actually run and test out of sample. The objective is really sort of the fitted model rather than prediction. So supervised learning, of course, thinks about prediction and the covariates, but this is quite different. It's sort of thinking about the interpreted model and what it looks like, really. Often the analysis is visual, where we actually just look at the components and figure out what they mean. So dementia reduction standard, if we think about just PCA or factor analysis, it's quite different when we think about biomedical data. And the reason is this. When we think about dementia reduction, it basically requires some sort of fixed N number of samples and a very large some sort of fixed G, or P, a large number of features or genes. But then the samples are going to be large and growing. So we can think about this in terms of like cat pictures on the internet where there's only, maybe 1,000 pixels, but there's many trillions of cat pictures on the internet. We can think about it as emails where there's a vocabulary that's fairly fixed. Those are our features. But the emails grow and grow and grow as we get more of them. There's millions and growing. We can think about it as newspaper articles where, again, we have a fixed vocabulary and the number of samples just keeps on growing. And again, the goal here is to take this large and growing number of samples and project all of them down to this two-dimensional space somehow. And we're going to do that by essentially taking this fixed set of features and figuring out how to combine them to think about how they work together. And basically projects each of those features down to just two of them, or some very small number. So why biomedical data is different is because in general the samples are small, and in fact they're often a lot smaller than the number of features. So when we think about dementia reduction in a statistical setting, the number of samples is basically required to be larger than the number of features. Simply because we want to make sure that statistically, mathematically, that what we're doing is the right thing. And I'll explain what that means in a few slides. But in this case, actually, our samples are usually a lot smaller than our genes or our features. So it causes a lot of problems, actually. Another thing that goes wrong in biomedical data is that the samples have a lot of structure to them. So in statistical settings, we often assume that the samples don't have that much structure. In fact, we assume IID, independent and identically distributed. And for biological samples, actually, they generally have a lot of structure. Structure could mean a lot of things. We're going to talk about that in the second half of the talk. But a lot of dementia reduction methods that I'm going to show you in the first half don't basically assume IID samples. And this is absolutely not the case. So there are reasons why dementia reduction is hard. That said, it is definitely one of the major workhorses of biomedical data analysis. So here's just three really high-level examples. Here's bulk RNA sequencing data, where this is a t-SNE plot, actually, looking at gene expression levels in 20,000 dimensions from about 52 different human tissue types. And you can see the clustering really nicely. And even though these labels were held out for the original dimension reduction, when we overlay the labels on top of each of the points, we see that there's very nice clustering among the different tissue types. Here's population structure. We're going to come back to this example in a little bit, but this is from a beautiful paper from November et al. In 2008. And they found that if they use genotypes, 20,000 or 200,000, sorry, genotypes from people across Europe, and each of these points represents the location of their 4 grandparents that all came from the same town, basically. You can see that actually in 2 dimensions, the principal components recapitulate the geography of Europe really nicely, which was kind of shocking at the time, but of course makes sense. And similarly, here's a single cell analysis where we're doing dimension reduction here. And again, even holding out the labels of the cell types, we see that this clusters really nicely into the different cell types here. So what can you do with dimension reduction? Why would we do it? Well, quite a number of reasons, I would say. So the first one, I think, which is sort of the ubiquitous one, is visualization, right? So first thing you want to do is be able to visualize this really high dimensional data, look at how these points are related to each other, right? Each of the samples. So again, that's why we do TSNE or PCA as sort of the first plot for every single huge data set that we have. Some people use it for smoothing, which I actually really like. And we do this a lot in EQTL analysis, where you think about, for example, running principal components analysis on all of your data. And then the first maybe 10, 50, depending on the size of your data set, the first principal components can be used actually to reconstruct a new matrix Y. You have the old matrix Y, you decompose it using PCA, and then you build a new Y hat, which is actually just the 2 low dimensional matrices multiplied together, where you're only using, let's say, 50 principal components instead of 2,000. That's a way to basically get rid of a lot of the variation that may or may not affect biological signal, but it's a way to sort of clean and smooth the data. Imputation of missing data is another thing that we can do in some probabilistic models, where essentially you have a Y matrix that is missing a lot of points. You can do probabilistic dimension reduction and actually, again, just do the reconstruction of Y hat, where all of the missing points in there are filled in by the expected values from the 2 low dimensional matrices multiplied together. Another thing that we actually do a lot in, oh yeah.
Can we have a question? So, sorry,
Yeah.
this is coming from me who doesn't know any biology. I'm curious, when you use like the 50 PCA components and
Yeah.
you drop the rest, like for biomedical data, do you worry about dropping the sort of
Yes.
outlier situation? And how
Yes.
do you compensate those situations?
Yeah, it's a good question. I mean, it comes up in a lot of different ways. It's basically an art and not a science. I wish I could tell you some official answer, but as you know, these low dimensional factors do not necessarily capture one thing, right? It's not necessarily, batch or population structure or something like that. It could be a combination of a lot of different things that are going into each of the factors. So when you remove one, you actually run the risk, like you're saying, of removing real signal. You can never guarantee that you're not removing real signal. So it's a problem. It's hard to do. Yeah. Good question. Okay. Yeah, vector quantization. I don't know how many people have heard of this, but from the machine learning standpoint, this is actually a way of doing encoding, where essentially you cluster the features offline and then project each of the sets of features to a low dimensional space. You can even do it just with simple mixture models, and it's often used in image analysis, for example, to encode images. We can control for confounders very similarly to the question that was just asked, but sort of also similarly with smoothing, where we might see that there are particular dimensions in PCA, for example, in our projection that correlate really strongly with batch or with the person running the experiment. And those things, often you can just remove them wholesale at the risk, again, of removing real signal. We can use it for prediction, sort of like I said before, where you're representing this high dimensional Y matrix with 2 lower dimensional matrices. You can predict in that you can put a new sample in there, see what the projection looks like, and reconstruct it, reconstruct that value for the Y sample again. We can find parts of the whole. So this is actually what we're going to focus on a lot here, where these representations in this lower dimensional space often mean something. And if they're sparse representations, in other words, there's only a handful of features going into each of these dimensions, and I'll show you what this looks like, then we can actually look at what those parts represent and see if they represent something interesting about the data. That's how we sort of find these patterns. The way I think about it, and again, I'm going to show you a lot of pictures of this, is that these methods really decompose variation. So we're very interested in variation and covariation among the features, right? We're interested in how all the genes interact, what the variation looks like. And we'd like to be able to explain that variation in terms of a number of different processes, whether it's experimental covariates like batch, like whoever the technician is that ran the experiment, or whether it's biological covariates like the population of the individual, or genotype of the individual, or something else related to that. So we'd like to decompose variation and then explain variation by labeling each of those components. Okay, so I argue that dimension reduction is undervalued in these analyses because it's just really hard to do correctly or right. Many of the problems I've listed below, but a lot of the assumptions that go into these models are not well characterized. So a lot of people use PCA or t-SNE without articulating exactly what the assumptions are of those methods. And then they run into trouble later when those dimensions are subject to incorrect assumptions, and they sort of can't back themselves out of it. There's no null hypothesis. So unlike statistical hypothesis testing, we'd like to, for example, say, what would these data look like without this particular pattern hidden in them, right? Without this particular source of variation. And it's really hard to do that. So it's hard to talk about a null hypothesis. Similarly, there are very few tests of statistical significance, right? We can't say how statistically significant a pattern is. We can often say how much variance it explains, but that's quite different than statistical significance. Often the conclusions we draw based on dimension reduction are not based on qualitative, but quantitative, are based on qualitative, but not quantitative evidence. So often we just look at clustering and explain why the dimension reduction worked in that setting, which is t-SNE or UMAP. A lot of those methods do that. I think the real issue that I think about, and sort of one of the major take-home messages from today, is that oversimplified or incorrectly specified models might miss biologically important patterns. So it's really important to think about which method you're going to choose and why, whether it matches your data set, whether it matches the questions and the patterns you'd like to extract from those data. And I think importantly, in the world that we live in, the results from dimension reduction are often really hard to evaluate. We don't have really quantitative ways to evaluate them all the time. They're hard to validate in the sense that it's hard to look at out of sample measurements to make sure that they're doing the right thing. And they're hard to reproduce in the sense that if we get two different samples from a slightly different population, often the principal components are way off from the original ones. So these are the problems. We're going to keep on talking about that. So I'm just going to do a really high-level overview of four dimension reduction methods that we use a lot in genomic and biomedical data sets. The first one is t-SNE. So this is t-distributed stochastic neighbor embedding model. I'm not really going to talk about this much other than to explain the geometry of it. But what I'll tell you is that, again, without giving too many details, basically t-SNE is just the KL divergence mapping Gaussian to a t distribution, okay? So here's a Gaussian 2D distribution. Here's a probability density. And here's a student's t 2D distribution. And what you should take home from this, although it's hard to see from these plots, these are just MATLAB plots, what you should take home from it is that actually the tails of the student's t distribution are much heavier than the Gaussian. So you can see also that the peak actually, if you look at the sort of equivalent of the y-axis, is much lower here. So this peak is much higher. So you can imagine that this is sort of a really peaky version of a Gaussian distribution. And what we're trying to do is sort of spread it out in the tails with this student's t distribution, okay? So to put it a little bit more bluntly, what we're going to do is, let's say we've mapped these points down to 2 dimensions, hypothetically. We choose a perplexity parameter, which basically just puts a Gaussian ball, I think of it as, around the particular point we're talking about. So here's the red point is the one we're talking about. Here's our Gaussian ball, which again, this ball size is determined by the perplexity parameters. And what KL divergence does in this case for Gaussian to T is it basically shrinks heavily any of the points that are within that Gaussian ball, right, to handle the sort of peakiness of the Gaussian, and it pushes away pretty strongly all of the points outside that Gaussian ball. So what that means is, if you've ever seen T-SNE with sort of perplexity too high or too low, you kind of get one of these extremes where either you have really, really tight clusters and it's just sort of a little too obvious, or whether you have really dispersed points in the space, right, where your Gaussian ball is just way too small in that case. Another thing that this sort of description of it explains is why you can't really go higher than 2 dimensions using T-SNE. So if you think about Gaussian balls, right, actually it's the case where in higher dimensions than about 3, I mean, especially if you get to like 10 dimensions, pretty much every single point is sitting almost exactly on that ball, just because of the way the confidence intervals work here. So basically every single point either shrinks right towards each other or disperses away from each other, given this KL divergence. So these are the problems with T-SNE, and yet it's still used pretty much ubiquitously well, a lot in genomics data sets. I'm going to talk about a slightly different thing today. I'm going to mostly focus on linear dimension reduction, where we have this very straightforward formulation. We have a matrix X, which is our, again, samples by features. And we're going to decompose this matrix X into a set of weights, lambda, and a set of factors, Z, okay? So this is the very, very, very high level version of what we're trying to do. And what I want you to note here is that the number of columns of Z and the number of rows of lambda are going to be small relative to everything else. So, you know, whatever the sample size are, whatever the features are, whatever those numbers are, we're trying to project to a much lower dimensional space. So ultimately, when you think about these 2 matrices, Z and lambda, representing X, we're going to be able to represent X in a lower dimensional space than the original data itself. And that's how it gets this sort of cleaning, data cleaning, decomposition kind of reputation, abilities, because of this lower dimensional representation. Okay, are there any questions about this? All right.
Can I ask
Oh yeah.
Can I ask a motivational question before we go?
Yeah. Totally.
So you mentioned earlier, like you have situations where you have labeled biological data. Like in those situations, do you still care about unsupervised methods, or could you just like, yeah, like what would be the advantage of that over something supervised?
Yeah, I'm going to give you 2 examples of that in the second half, if that's okay. It's a really good question. It's actually one that I've been like hitting my head against the wall for 2 years now, and I think we just came out with a couple methods that actually start to address that. But is it okay if I put that off for a little bit?
Yeah. Totally.
Okay, great. I'll show you how we do that. Yes, yeah. So again, this makes all the sort of assumptions that we know from statistics, where each of the samples here are going to be IID, and we haven't talked about the distributions yet and the distributional assumptions, but we're going to specify those next. So the most common, I would say, dimension reduction method in the world probably is principal components analysis. I'm specifically focusing on the probabilistic version, which is from Sam Royce, 1998, and then Tipping and Bishop in 1999. The idea behind principal components is that it takes, let's say, this 2-dimensional space, this 2-dimensional data set, and it pulls out the directions that maximize variation. So principal component 1 is going to be this vector right here. that basically maximizes, identifies the maximum variation in these two-dimensional data. Then principal component 2 is going to be this vector right here, which is by definition the orthogonal one to the prior one, but it sort of gets the second dimension. And we're going to keep talking about what this means in pictures. PCA, whether we want it to or not, makes very strong Gaussian assumptions about the data. And there are versions that relax that, but there are strong Gaussian assumptions when we think about PCA generally. In this case, both Z and lambda are going to be in the reals. So they're going to be positive and negative. Some might be 0. In general, there's little sparsity though. So when we think about these two matrices, Z and lambda, we're going to see very few zeros in them. So in other words, when we think about each of the factors, they're going to basically explain a lot of variation in all of the X's, in all of the different samples. Similarly with lambda, they're generally going to be composed of, I think of lambda sort of the weights on the features. Each factor is going to be composed of pretty much all of the different features in the X, the original X. So little sparsity, hard to interpret sometimes. So one way to think about PCA that's different than the two that I sort of just referred to previously is a way to minimize reconstruction error. So here we basically like to choose the Z and the lambda variables that minimize the distance, the reconstruction error between X and Z lambda, okay? So again, a very toy example of this is that we have X in 2 dimensions, right? X1, X2, here are all of our red points is X. And we'd like to find the principal component, the space that that maximizes or minimizes the reconstruction error, sorry. So the way that we're going to do that is, let's say this is our perfect principal component here, this orange dotted line. And this is going to be the line where if you project each of these points directly to the line, then the points that are sitting on the line, these are going to be the lower dimensional projection, right, of each of these points. The distance between the original point out here and the projected points here is going to be the smallest. Okay, so we're trying to, again, choose this line that where when you project all the points to that line, it minimizes the distance, the residual. That's reconstruction error. So that's sort of a third way to think about PCA. When you actually look at what happens in PCA, I'm going to show you a bunch of examples of PCA and other things. But when you look at what happens with PCA, you get these things that people call eigengenes or eigenfaces. They're basically going to be sort of meta representations of different sort of classes of, in this case, pictures of faces across your sample. So here you can see a lot of positive, these are the dark weights, and negative, these are the very light weights, pixels in these regions. And you can see different eyebrows appearing across the different samples. You can see different types of chins. You can see the mouths in different situations, bigger upper lips or smaller upper lips. Eyes are obviously slightly different as well. Hairline is going to be different in each of them too. So again, these are sort of referred to as eigenfaces, but again, you can just sort of add them up. This is the example. You can sort of add up each of these eigenfaces with weights on each of them, and then you're going to get the full picture. Okay. This is actually an example from Lee and Sung in 1999. This is their non-negative matrix factorization paper, which we'll talk about next. But again, if you look at eigenfaces here, the first thing PCA will do is get the mean face. So this is literally the pixel average of every single face. And then when you think about what it does next, you can look across the other eigenfaces and you can see, well, the first one actually differentiates the right side from the left side, right? You can see red there and bluer there. And then you can see sort of top and bottom being differentiated. So it kind of does differences from the average, right? Where the average is, again, the first principal component. Okay. And then again, every single face is going to be some positive or negative weighting of each of these different eigenfaces to create the whole. But overall, this is going to be a much smaller representation of the data than the original, 100,000 pictures that we had, right? This is going to be fairly small. Here's an example that I show in my class that I just really appreciate. So what these researchers did is they grabbed a whole bunch of scary things, right? These are called risk factors, whether it's nuclear war or microwave ovens. And they gave a whole bunch of people a survey about how scary they were, what they were scared about. And then they just ran PCA on the survey results. And I thought this was just so fascinating. So here's a rotated version of their principal components, but what you can see is that there's kind of really interesting labels on here. So over here, they call it dread risk, where it's like nuclear weapons fallout, nuclear weapons and war. There's a lot of really scary stuff there where, you know, we're not going to survive very well. Here, it's kind of the opposite, where caffeine, aspirin, these are sort of like necessary evils, I guess you could say, where they're not necessarily that terrifying and the effects aren't going to be that big. Axis 2, they've labeled the risk, right? Here, the unknown risk, where we really don't know what's going on with DNA technology. This is from like the 1980s, I should say. And microwave ovens and nitrates, we know a little bit better now, but not perfect. Whereas over here, we know exactly what happens when you set off some fireworks or you blow up a dynamite or you have an auto accident, right? There's nothing unknown about that. So I love the way that these sort of fell out and in terms of thinking about the relationship between each of these different risk factors. And again, they sort of separated them into dread risk versus unknowable risk. And I'll ask you this question now. It's sort of think about how you might do this. One of the sort of essential steps in dimension reduction is to essentially label and interpret each of the factors in the dimension reduction. So think about how you might do that in genomic data, in biomedical data generally. But here we can just sort of eyeball it and see label these two factors. The next method that I wanted to tell you about is shockingly straightforward and also shockingly powerful. It's non-negative matrix factorization. So again, this was developed by Li and Sung in 1999. And the idea here is really just to take a non-negative matrix V, right, and decompose it into W and H. And the only rule here, the biggest rule here, is that W and H are non-negative. And in a bunch of follow-up papers, they explain how to do this very, very fast. So you can actually do non-negative matrix factorization for very large matrices V. Also, you can have a probabilistic interpretation of it. We're going to talk about that a little later again. But the key again is that W and H are both non-negative. So what this does, interestingly enough, is this non-negativity constraint encourages extreme sparsity. And the reason things are so sparse is because you can never subtract anything, right? You just have to add to get the final result. So there's sparsity in two dimensions here, right? There's both sparsity in the number of features that can be involved, because you kind of need sort of the minimal building blocks to be able to represent everything with no negativity without being able to subtract any of these factors. But there's also sparsity in the number of factors that explain any of the samples, because again, you don't want to have to use all of the different parts to be able to explain every sample. Just thinking about it in terms of the constraints here. And again, the geometry, the non-negativity is why this happens. We're not, just like PCA, we're not going to see the first factor here being the mean, because again, we can't go both directions from the mean. We can only build up. So this leads to what people in dimension reduction generally call a parts-based representation. This gets at something very, very different than PCA. So here's another example also, here's an example of NMF, non-negative matrix factorization, from the same faces example that you saw from PCA before. And again, what you see is something very different. The dark areas here represent one thing, right? Whether it's a mouth or a mustache or one side of the face or a particular region in the forehead or a chin or right underneath your nose or your eyes, it's going to be a part, right? Which is just, I think, so cool. And you're going to see a lot of sparsity here too, right? There's a lot of things, pixels here that have no weights on them at all. And similarly, in the factor matrix, you're going to see a lot of sparsity there too, where the parts that represent this original face are drawn from only a handful of the parts represented in the NMF decomposition. Okay, so this is another thing with this totally different set of behaviors. Here's an example that again, Lee and Sung put on the non-negative, or put on an encyclopedia data set. So this is just a set of words, well, a set of articles about things like the Constitution of the United States. And here's 4 sort of representative factors where each of the words here are the highest, or the 10 highest represented words for each of these factors. And you can see, here's court, government, council, culture, supreme, very sort of government. Here's president, served, governor, secretary, state, elected. So this is more about, elections and things like that. So in order to describe the Constitution, we see that we're going to weight these top 2 factors, and we're going to be able to describe the words that we see in this encyclopedia entry. We don't see any representation from this flower factor or these disease factors. Basically, no words need to be built into this to be able to explain this encyclopedia entry. Okay, so that's how NMF works.
Can
I'll
I ask
add-
a question?
Yeah.
So going back to the last 2 slides, do you have to give the weighting matrix, and how do you decide how to weight it?
Yeah, a lot of these dimension reduction methods, so you don't give it anything. You only give it the original samples by pixel values. That's literally it. For this example, for the words example, you just give it samples or articles, let's say, by a vocabulary, and each element is going to be the count of how many words of each of those vocabulary words exist in that article. So the dimension reduction is all done by the method. In this case, the dimension reduction is done by constrained optimization. In PCA or some of the other models we talk about, we can do it in terms of optimizing the reconstruction error. We can also do it probabilistically by forcing certain priors on the factors and the loadings, and just running statistical inference. So nothing is given besides the original matrix. It's kind of astounding that this works so so beautifully, but it really does have to do with the constraints of the problem, the geometric constraints. It's quite amazing. Yeah, it does. I have to say, the first time anyone hears about, I think LDA actually, this latent Dirichlet allocation, it really does genuinely feel like magic, just because the results are so so clearly the way we think. And I think that has to do with a lot of sparsity, but you really don't give it any information beyond the original matrix. So the world kind of changed, I would say, in 1999, and then again in 2003, when these 2 latent Dirichlet allocation papers came out. So the Pritchard, Stevens, Donnelly paper in 1999 basically was entirely the same model as the Bly et al. In 2003 paper. And yet they basically didn't know about each other for about 4 or 5 years, until all of a sudden worlds collided and they realized it was the same model. And both of these papers by 2007, let's say, had about 10,000 citations each. They're all they're both very popular methods, but they are the same model at the end of the day. So topic models identify basically a small number of words or features to capture each topic or factor. And then, just like in NMF, it identifies a small number of topics that explain each document, where now a document is going to be a sample. The topic proportions sit on a simplex. So we can do cool things like this, where let's just say for a particular sample here, we can actually describe in terms of proportions how each topic or factor explains that particular sample. Both of the decomposed matrices end up being very sparse, which I'll show you some examples of. That mostly is a function of the likelihood of the data, and I'll talk about that offline if you want me to. It requires non-negative a data matrix. The original X matrix is going to be non-negative. Yeah? Question? Okay. Probably feedback for me. Okay, so this is what the model looks like. And oh yeah. Mm-hmm.
I was just wondering, all the images are in black and white. Is there a reason for that? Is it like different?
Oh, is this black and white?
I don't know, the previous images. Like
oh, the 3D. Oh yeah. No, they can be anything. You can do different channels of pixel colors or anything you want. Yeah. Does that answer your question?
Yes, thank you.
Okay, great. Okay, so this is the model. And really the thing to take away from this is that our two matrices Z, this is our Z matrix, just like before, which is D by N, the number of dimensions, times N the number, or by N the number of samples. And then beta is going to be our loadings matrix, which basically describes the K words. This is our vocabulary by D, which is going to be the, again, the number of, documents. I'm saying it wrong, but yes. Oh, sorry. Let me try this again. Theta here is going to be the factor matrix, which again is, which appropriately is going to be number of documents, which is the samples by K. And then this beta is going to be the number of vocabulary words or features by K, the number of topics. And you can see that there's Dirichlet distributions on theta and beta. So both of them, again, are going to sit on a simplex, which means that each column of both of them are going to be non-negative and sum to 1. And then the Z and W distributions are both going to be multinomial values there. So here's a great sort of representation of LDA that I kind of love from the original paper, the Bly paper. So the idea here is that we'd like to explain every single word in this this document here. This happens to be a genetic document. But the idea is that every single word we have is going to essentially be assigned to one of the topics that we have. And here the topic that explains, let's see, organism is going to be topic 2, which is sort of some combination of life and evolve and organism. Topic over here is going to be genes, or the word over here is genes. And this is going to be explained by the first topic, gene, DNA, and genetic. Some other ones might be computational, right? Where computational is certainly not going to be explained by those first 2 topics. It'll be explained by this one. And then when you look over all of the words in the document, right, you're going to be able to look at a set of proportions that explain how each of these words were sort of generated in this document. So now this document, again, can be said to be made up of 3 different topics, right? It's going to be DNA, it's going to be evolutionary biology, and it's going to be computational biology. And again, it feels sort of like magic the first time you hear about it, but this is just a function of the likelihood that we put and the constraints that we put on these parameters, and you can pull this information out really nicely. And there's a lot of sparsity in this model too, as I said. So here's an example from Rosenberg et al. In 2003. Each of the columns, the sort of, you can sort of see the pixelated columns here, is going to be a single individual. This is going to be their genotype. This is the HapMap data set. And what each of the colors represent is either K equals 2 populations up to K equals 6 different populations, being able to describe the genotypes that we see in each of these individuals. And you can see that the populations that we identify very much match population ancestry. So here is a lot of the East Asian populations. Here we see a lot of the South Asian populations. Here is going to be European, and here is going to be African populations. And there's actually a bunch of Central and South America where if you go deep enough in terms of the number of populations, then you can see sort of unique populations coming up there, which is specific to Central and South America. I'll show you an example from one of my papers that I thought was kind of crazy when it actually showed up on my screen, but here it is. So this is from actually the Novembre et al. 2008 paper. They measured 1,000 individuals at about 200,000 genomic locations, and they measured them all across Europe. So every single one of these 1,000 individuals had 4 grandparents that they could locate to essentially the same place in Europe. The linear projection of this enormous matrix was pushed down to 2 dimensions. So here's 3 different examples of that. And of course, as you can see, the projected data definitely do a good job of recapitulating Europe. So you can see Spain over here. Here's the UK in purple in each of these, or sorry, in green. And then over here we see Greece, for example, and Italy. And actually, you can see some of the islands, which are just absolutely amazing. We set Cyprus, yeah, all these 4 points or 5 points over here, and these 4 points over here. In every single one of these projections, keep coming out of the the standard clustering, which is, I think, quite impressive. So the one thing I wanted to say was, as much as they do very different things, they have very different objectives. Actually, the results you get from 3 different methods are quite similar for these data. So here's principal components analysis, where you see a fairly tight mass of this clustering. Here's something that I call a sparse factor analysis, where you can kind of see these the rotated versions to match the map of Europe, but these are zeros in the sparsity, but you can still see a map of Europe really nicely. And then this is actually the LDA, latent Dirichlet allocation model, where in this case, as opposed to having 2 factors, we actually put 4 factors representing each of the corners. So even though we had to have twice the number of factors, we can actually pull out that map of Europe really nicely. But you do see more sort of regularization. This is going to be shrinking to 0 in each of these different dimensions, just because of, again, the different assumptions in latent Dirichlet allocation. Here's another example from a recent paper from 2021 from Corinne Pelka's group. And the idea here is that they have a really large number of single cell sequencing cells from an RNA sequencing from tumors, from specifically colorectal cancer tumors. And they did 2 types of analyses, right? They did t-SNE up here, which you can see gives you a lot of really interesting clusters, all these lines. And what they did was then within each of the clusters, they labeled the different cell types with the actual cell type labels. This is, of course, information that's kept out when they're doing the original t-SNE. And you can see, of course, that it corresponds really, really nicely. And actually other aspects of these cells also correspond fairly nicely. This one's a little less nice. They also ran non-negative matrix factorization. And the results were, this is just the t-SNE projection, but they colored each of the cells that are made up of each of the different sort of gene programs or parts or factors from NMF in each of these pictures. And you can see that these are very specific gene programs that each of these factors identified. Here, it's just going to be a small set of cells over here and down here in stromal and myeloid cells that exhibit this particular part, this particular gene program. And you can see that, again, it's going to be gene programs that are kind of found ubiquitously. I really like this picture because I think it does such a good job of explaining how, or like fundamentally different, t-SNE is from the NMF type of decompositions. So are there any questions at this point? I'm going to go on to probabilistic versions.
Barbara, can you hear us?
Yeah.
Okay, you can hear me. Maybe we'll just have to pass this. There are some questions, but I don't know that our mics are working. So
Okay.
who had questions? I'll give you this mic.
I had a question about a few slides back about the Europe. Yeah. Do you know by any chance how they managed to get the locations of the clusters to manage the physical location?
I mean, that's entirely the structure in the data. So looking at it just from principal components analysis, right? These were literally the 2 principal components that explained the most variation in this genomic data, right? And those, and again, mapping it down to 2 dimensions, it just happened to perfectly match in 2 dimensions, the geography of the space. Of course, this represents sort of evolution in space, showing that there is quite a lot of structure, actually, quite a lot of variation in genotype data, even for people who populations that live right next to each other.
Interesting. Thanks.
Hi. Basically, my question is, what type of guarantees can we give when using this type of methods like t-SNE? Because by playing around, it seems that you can basically make this pretty picture somehow from any kind of data set.
That's right. Yeah, I mean, I think there, give or take, no guarantees, right? So just because your reconstruction error is low, or just because you've minimized the KL divergence between, a Gaussian onto a T-distributed system doesn't mean much, right? I mean, it means what it means. There are no guarantees in terms of the interpretation. That's the problem, right? So again, thinking about it as decomposing variation, there's no guarantees that it's going to sort of align with a particular type of variation. There's no guarantees of sparsity, even though sparsity generally happens in these non-negative models. You have very few guarantees. You just, when I think about doing these analyses, I really think about just taking the assumptions that we know that they have and sort of putting them onto the results, trying the results 100 different times in 100 different ways with many different normalizations, many different factor numbers, and just making sure that there is some sort of reproducible signal that comes out of them. Because like you said, there's very little guarantees. This is part of why it's hard, because it ends up being more of an art than a science sometimes.
I have one more question about the Europe data. So the clustering method is separate from the dimensionality reduction here. So you might have mentioned it, but is this like a k-means or something?
Yeah, no, so actually it's not. So what we've done here is just projected each of these samples, these 1,000 samples down to 2 dimensions. And then what we did was we overlaid the location, the geographic location of their 4 grandparent ancestors on top of that. But the 4 grandparent ancestors were held out, the locations were held out in the dimension reduction. Does that make sense?
Okay, so those colors are known labels. They're not from like.
They're known labels, but they were
Okay.
held out of the dimension reduction. Exactly.
Okay. All right. Thank you.
Good. Yep. Cool. Other questions?
I don't see other questions. I think you can go on. Thank you so much.
I'll go back to that really quickly though. That's one thing you can do with dimension reduction is basically, project everything down and then do like k-means clustering or whatever you'd like to do in the lower dimensional space. People do that a lot, just to be able to not have this really high dimensional distance matrix. You can just do something really easy in the lower dimensional space. Okay. So I wanted to tell you a little bit about my work. We're going to go fast through this just because it's a bunch of sort of thinking about dimension reduction generally. And the way I think about it, like I said, is this probabilistic way. If you have questions, stop me. I'm happy to talk about it afterwards. So when I think about dimension reduction, I think about it probabilistically, where again, you have this Y matrix, which is going to be features by samples, N by P in this case, or P by N technically. I've transposed it from the standard because of the big data problems. So what we're going to do is decompose that into a set of factors, a set of factors X, which is going to be K by N, and a set of loadings lambda, which is going to be P by K, okay? And the way that we think about this just in terms of very vanilla factor analysis is that each of our Y, I, J elements, so a single point in this matrix, is going to be able to be described from a Gaussian, where the mean value is going to be the product of the appropriate lambda and X factors, right? Each of the K factors there. And the variance term is going to be J specific. In this case, J is going to be gene specific. So every single gene is allowed its own variation, okay? So yes, so that's the probabilistic model. I'll add over here that this epsilon or Gaussian noise, this is just going to be the assumption that this is going to be mean zero, variance term tau inverse. So this is epsilon. It should be white noise if we're doing it right. So it turns out that in this very vanilla version of factor analysis, actually the data likelihood is invariant to orthogonal rotation, scale, and label switching. So let's actually talk about each of those really quickly. So when we think about actually, maximizing likelihood to be able to get the values of lambda and X using expectation maximization or something like that, we are going to find that actually we can describe the likelihood of Y after we rotate, do orthogonal rotation on each of the lambda and X variables. In other words, if we have a matrix that will rotate lambda. We can actually rotate X by the opposite direction, and we can get the exact same likelihood for Y. Similarly, we can scale all of our X or our lambda by A, and then scale each of our A or X by 1 over A, and we can also get the same Y. So that means scale doesn't really matter here. And finally, we can do label switching. So if we shuffle K, each of the columns in lambda, and we shuffle X column or rows in the exact same way, then we actually also get the exact same likelihood of Y. So this is kind of troublesome because every time you run some kind of factor model, you're going to get completely different lambda, completely different X, and the Y axes, thinking about the values of them really don't mean anything, right? So these invariants basically mean a bunch of things, right? They mean the factors are going to be correlated. They mean the factors are not going to be comparable either within or across different applications. And it might mean it's hard to sort of label the factors in a meaningful way, as we sort of referred to before. I'm going to keep talking about that though. So this is hard to do because again, it feels more like an art than a science. So how do we actually get over these challenges and make these methods easier to use across different applications? So one thing we can do is add sparsity. This creates both interpretability and also rotational invariance. We're going to talk a little bit about that later. That's also why these non-negative models are sometimes really fun to look at because of this parts-based representation that ends up being very interpretable, very sparse. We can also study structure that's invariant to matrix rotations. I'll talk about that then in a second. And we can actually take interesting patterns and test these hypotheses using held out data. That's how we can actually think about this information. And I'll give you some examples of that later too. So here's the first idea, right? Which is what happens if we put a lot of sparsity in here. So sparsity basically just means if we look at one of these columns in lambda, it just means we're adding a lot of zeros. So we can do this in a frequentist way by adding some kind of L1 penalty, for example. We can do it in a Gaussian way, or a Gaussian way, sorry, a Bayesian way by adding a distributional assumption to lambda prior that encourages sparsity. So here we can think about actually regularizing in 3 different ways. We can regularize globally, which basically tries to shrink every element to 0 in lambda. It's not too helpful, actually. We can do it factor-wise, which actually just includes or excludes a lot of factors. It ends up removing a lot of components, but there's no sparsity within the components. Or you can regularize locally, which means literally every single element of this lambda matrix is going to be encouraged to go to 0, but separately. And so local is generally what we do here, just because it actually creates sparsity in lambda. And then we get these really nice, really interpretable lambda matrices, where when you think about a single column now, a single factor, there's only a handful of genes that sort of make up that factor. So now we can look at that small set of genes and interpret things like, what do those genes have in common? Why are they being pulled out here? What samples are they over or under expressed in? And what does that tell us about those samples? So there's a lot going on here that is fun to play with in the results. So what do they really represent? This is getting to the interpretation that I really like to have in my mind. So what we're doing in my mind when we do dimension reduction is actually, depending on the dimension reduction, but this is the sort of PCA version of it. Well, actually, it's not PCA. This is the factor analysis version of it. So the idea is that we'd really like to understand the covariance matrix of Y. And remember, this is going to be samples on the columns by genes, the features in the rows. So this covariance matrix of Y is going to be huge. If we have 100 samples, we may have 20,000 genes, and there's no way we can just describe the empirical covariance of Y, right? It's just 20,000 genes by 20,000 genes. We can't get that from a 20,000 by 200, let's say, matrix. It's not possible. I mean, you can do it, but it's not going to be correct in very many senses. So what we want to do is essentially do dimension reduction on this, right? So when I think about what these factors represent, if you actually integrate over the factors themselves, you're left with the loadings lambda times lambda transpose, right? This is going to be the description of the covariance of the off-diagonal elements of Y, plus some sigma, which is actually going to be the diagonal variance terms, okay? So this is an absolutely beautiful result. And at the end of the day, again, what I think about when I think about these loadings is actually they're just a low dimensional representation of the full covariance matrix of Y, a gene by gene covariance matrix of Y. And if you multiply them together, you're going to get this really nice, usually non-singular. I've done this many, many times, and it's basically always worked, non-singular matrix describing the covariance of Y, the gene by gene covariance of Y. It's non-singular because A, we have this really low dimensional space here, and B, we also add this diagonal variance term. All of those things go to make this a non-singular matrix generally in practice. We can add more sparsity. There's nothing preventing us from doing that. So actually Bayesian biclustering is when you additionally add sparsity to X. So if we do that, now what we're saying is that for each factor, there's actually only a handful of samples now that factor is variable in, right? So actually we did this, one example that we did for this is actually do genes by samples decomposition, where we found a factor that only occurred in smokers. And so we were able to say that actually here's a set of genes that only co-vary in the smokers that we see. There were lung associated genes, and presumably it had to do with damage to lungs during smoking. But you can again interpret these factors in this low dimensional space by looking at what all these samples have in common and comparing those samples, looking at their metadata, their demographic data with the features with the factors themselves, I should say. So this is kind of a cool application, I think, of these types of models. But even more important, I think, than the cool application is actually this representation. So again, this is the picture I see when I think of dimension reduction. I see Y here, right, which is going to be, again, genes by samples. And what we're doing when I think about when we do dimension reduction is basically partitioning variation in this space. So in particular, here's a factor, a single factor, where the variability in this set of genes, non-zero genes, and this set of samples, again, the non-zero samples, is going to be explained, all the variability in those genes and samples are explained by this particular factor. Not all of it, but some part of it. And then when I look at each of these factors, then I would like to explain I would like to use that explanation to describe a particular contribution to variance. So maybe this is the smokers, and these are just going to be the genes that are affected differently, that co-vary in smokers differently than non-smokers, for example. So now I want to, given this representation, I'd like to, again, put labels on each of these factors saying why only a handful of genes and only a handful of samples appear to co-vary, okay? So when we think broadly about putting these labels on each of the factors, we have to go through a lot of different possibilities. So there's a lot of held out data, a lot of data that did not go to this. So we might think about technical covariates, like the batch of each of these samples. Could be library prep, it could be the technician that literally ran the sample. We can also think about biological covariates, so tissue heterogeneity, the makeup of different tissues, but it could also be age, sex, BMI, smoking status. Population structure actually contributes a lot of variation to gene expression in particular. So when we think about the ancestry of each of the samples. And then what I love a lot is genomic covariates. So it actually turns out that differences in our genomes actually contribute a lot to variation, it turns out, in genes in the population sample. And it's fun to try and identify particular genes or genes that are regulated by genomic covariates. So that's always kind of fun. So again, our job after doing this dimension reduction, partitioning these sources of covariation, is then to give each of them a label, right? To be able to describe which type of variation this particular factor represents. Another thing we can do, I think this is my last of many different versions of factor analysis, is something called canonical correlation analysis. So this is where we start getting into multimodal data sets, decomposition with data sets that represent two different types of observations. So here, for every sample, we have two things, right? We might have gene expression data and genotype data. We might have gene expression data and imaging data. We can have a lot of different things in Y1 and Y2. The key is that there's the exact same number of samples along the columns, okay? They can have very different feature numbers too. So P1 and P2 can be very different. There can be 20,000 genes and only 100 or 1,000 features in P2 for images, let's say. So what we're going to do is we're going to take these two matrices and we're going to project them down to X. X here is the same feature set, okay? So this is identical matrix in these two different representations, but they're going to have their own error, right? That error has to do with their sort of modality specific error, and they're going to have their own weights, okay? So each of these weight matrices, these loadings matrices, are going to take a different set of features, obviously from Y1 and Y2 respectively, to be able to create this shared latent space X, okay? Whoops. So then when you interpret these models, and again, we can throw sparsity on lambda like we did before, then what we can do is, let's say we're looking at a particular factor, there's only a handful of features here, and there's only a handful of features in the second data modality here that go to produce that particular factor. So what that means, again, is that these features and these features are going to tend to covary. They do covary in terms of these paired observations, okay? So that gives us a lot to work with in terms of patterns, in terms of thinking about follow-up studies, where now we're interested in quantifying how these subset of features in P1 or Y1 and the subset of features in Y2 covary, right? So that's the fun part of canonical correlation analysis. I'll say one more thing, which is in all of these methods for dimension reduction, I've shown you a bunch that have to do with Bayesian latent factor models. They're not necessarily the most ubiquitous, but the reason I use them is because they're sort of the tool that I know how to work with really well. So I think there's in general a trade-off between expressiveness, how expressive you can be with your model, and these can be extremely expressive. You can mess around with them in a lot of ways, and computational tractability, where sometimes it's really hard to scale these models to large data sets. Is there a question? You're good, okay. So in general, in my work, we choose models that are expressive just because of this big data problem. If we use autoencoders and other methods for dimension reduction, we are in this sample limited feature rich space, right? The P much greater than N problem, where we don't actually have that much many samples. So when we think about these data hungry methods like deep learning, it's often really, really hard to have enough data to be able to fit these models appropriately. But since machine learning and statistics in general are developed in these big data contexts, I think it's really up to us as people who think about machine learning specifically for biomedical data sets to reimagine all of these approaches in the context of high dimensional data, not big data, right? High dimensional data where P, the number of features, is much greater than N, the number of samples. And it's often true in these contexts that you need really structured models to be able to recover the biological signal that's interesting in those data, because there's a lot of confounding going on. And unless you sort of pinpoint exactly which signal you want, it's often really hard to be able to see that in the dimension reduction. I'll give some examples of that in a little bit. And then, as we said before, the fitted model has really interesting mechanistic interpretations, and the uncertainty is explicit, which is all really nice. In terms of how to achieve computational intractability in these models, there's actually many ways to do it. There's a huge amount of research focused on approximate inference, which we take advantage of heavily in my group when we're actually fitting these models to data. Okay, I'm going to talk a little bit about some work that came out of my group recently. We're going to, I have about 20 minutes left. So are there any questions at this point? This has to do with structure in the samples. Yeah. Okay.
Oh, sorry,
okay.
we do have a question, but our
Okay.
mics aren't working, so let me run over.
Sorry.
Do you use any data accommodation techniques in order to enable some machine learning methods?
Actually, no, not really. So you can do sort of semi-supervised versions of it. And I guess what I'm going to tell you now is sort of a semi-supervised version of a lot of these methods. But in general, for everything that I've told you up to this point, no. No data augmentation. Again, every once in a while you can do imputation of missing data and things like that, but nothing I've shown you so far requires any of that. Yeah. Cool.
Sorry, one more question.
Thank you. I didn't get your comment about like the rotational invariance. Like in what sense do we have rotation?
I mean, just to have you can have an orthonormal rotation matrix, right? And you hit it, lambda with that, k by k orthonormal rotation matrix, and you then invert that and do it the opposite. Well, actually, you don't need to invert it. You just do it the opposite direction with the X matrix, or the Z matrix, I guess, and the factors. And then again, it ends up being the identical description in terms of the sum over the factors to describe the data. Does that make sense? Could write it out.
Yeah, that makes sense. But why is that a bad thing? Like, it seems.
Well, it's a bad thing because a lot of times we label the factors. If it turns out that those factors are not interesting, if you can just rotate the factors, right? So the example here of the spatial coordinates, right? These factors don't mean anything, right? The point is that we can easily take the PC1 and PC2 in this setting and essentially rotate it like a clock. And all of those are going to have the exact same likelihood with the data, it turns out, if this is probabilistic principal components. So why? Well, again, if you label one as like the north-south axis and one is the east-west axis, that all goes out the window in the next run, right? It could be, the likelihood is identical, whether it can be any direction, basically.
Okay. Yeah.
Sense?
Thank you.
Yeah.
Any other questions? No. All right, go ahead, Barbara.
Okay, great. Okay, so a little bit on structure in the samples, which I think is a really interesting problem in, of course, there's a lawnmower about to start, a really interesting problem in biomedical data sets. So we might find, for example, that we have actually case control structure in the samples, where some set of samples are cases, let's say they've been treated by something, they have a particular disease, and another set is controls where they haven't been treated or they don't have a disease. As you saw before, we have spatial coordinates where in general, we leave those entirely out of the dimension reduction and then we overlay the colors on top of those coordinates, the projected coordinates. We can also think about this with batch or assay or perturbations where we do stuff to a set of cells or they occur in different batches. And then we'd like to look at that structure. Similarly with cell types, here's comorbidities, which is essentially sort of I think about it, this is case control. We can think about it as sex labels. So this is going to be males and females, where actually in the low dimensional space, it looks like they're very structured there. And also time, which is actually quite similar in terms of spatial coordinates, but it's now across time and not space. So let's sort of be specific about this since we're doing this in terms of machine learning. So case control and sex and comorbidities end up having binary labels, control versus case, males versus females. Continuous labels happen in the context of time and space, right? And then categorical labels happen for batch or perturbation or cell type, where there's not really a relationship between those things. They're categorical variables. So we kind of want to think about all of these different types of structure when we think about the samples, which means we have to basically develop a whole new language of models to be able to describe each of these, each of the structure in the samples. So the first example I'm going to give is case control studies. So here's an example of principal components analysis projection of these high dimensional gene expression samples into a low dimensional space. And you can see In no therapy, you see actually quite a lot of structure here, whereas in therapy, a lot of that structure goes away. It's just kind of one big blob. And we'd like to do a better job of understanding what's going on in these PCs. And the way I think about it, this is a sort of general idea behind contrastive models, is that we'd like to subtract out all of the variation that we see in the controls, and then look at the variation that we see in the cases without that control variation, okay? So again, here's the cases with the therapy, see no structure there. Here's the controls. We do see a lot of structure there, but presumably a lot of that structure is shared. And then when we remove this variation from here, we end up seeing, again, a lot of structure in the cases that we wouldn't have found if we hadn't subtracted, in some sense, the variation from the controls, okay? So very briefly, the contrastive setting looks something like this. We have two matrices now. We have the background information, which is going to be P by M, and we have the foreground information X, which is going to be P by N. And this is interesting because they share P, right? They share the number of factors. I'm so sorry about that. If you can't hear me, let me know. They share the number of factors, features, but they might be different, non-paired samples in terms of the number of samples. And again, this is going to be the controls over here in the background data. They're going to be generally healthy or whatever control samples. And then these are going to be the foreground samples or the treatment or the disease samples. And again, our goal here is to characterize variation that exists only in the foreground and is not shared with the background. Whoops. Okay, so here's a really simple example of this. So here what you're seeing is the background samples in gray. This is just in 2 dimensions, and the foreground samples in red. And you can see that the principal component, which is what we've plotted here, is just going to describe, right down the middle of the sort of 0-1 line, describing the direction of maximal variation in foreground and background samples. But ultimately, we don't care about that, right? The structure in the foreground samples is very clear when we highlight them, and it's in the exact orthogonal direction. So what we really want is one of these contrastive models where we essentially remove that first direction of variation that's shared with between foreground and background, and what we're left with is the actual structure in the background data, in the foreground data, sorry, where we can very clearly distinguish 2 clusters in there. So that's sort of the very low dimensional interpretation of what we're trying to do. So the way that we do this, or actually I'll say that the way that prior models have done this, there's contrastive mixture models from 2013, contrastive PCA models from 2018, and then more recently, or fairly recently also, contrastive latent variable models from 2018 as well. And again, the general idea is that there's going to be, in the background and the foreground data, there's going to be some shared component of variation. And then in the foreground data, there's going to be foreground specific information as well. And that's all going to be contained within the dimension reduction model. So we developed something called probabilistic contrastive PCA right over here. And I'll say that it works, it's sort of a generalization of probabilistic PCA models, which we talked about a little earlier, and these non-probabilistic contrastive models, or sorry, the non-probabilistic contrastive models. An extreme version of this is just principal components analysis, just the straight optimization. So the model that we developed looks something like this, where these are, again, the exact same matrix decompositions that you've seen before, where X is just going to be decomposed in terms of W and ZX, and Y is going to be decomposed in terms of W and ZY. And here again, this is the background, and this is the foreground, okay? So the crazy part about this is that we actually don't have anything that's specific to the foreground data. What we do is we do this, well, it's contrastive. We're calling it now a relative likelihood. So here, we're describing the maximization of our different parameters in this model, W and sigma squared, where we maximize the foreground likelihood and we actually minimize the background likelihood. So that means that W will uniquely not be able to describe Y, whereas it will be able to describe all of X that isn't shared with Y, basically, where the variation is not shared with Y. It's something goofy. It's not a relative likelihood or a likelihood, sorry, it's not a likelihood ratio because likelihood ratios consider the probability of different models with the same data. And it's certainly not a likelihood because we're actually minimizing a particular type of likelihood. So we call it a relative or a contrastive likelihood. As I said, PCPCA actually generalizes to a probabilistic principal components analysis when we set the scale variable gamma right here to 0. So we basically get rid of the denominator. And when sigma squared goes to 0, then we get these non-probabilistic versions. In the limit here, we get these non-probabilistic versions of these models. And of course, if you do both of them, you just recapitulate PCA. So we can actually simulate this, or we can do this with this toy problem that I told you about. So here's probabilistic PCA, where again, we basically get this direction of maximal variance exactly as we expected. When we start cranking up our gamma variable, we actually are able to recover this exact foreground specific variation in this version of it. So that was sort of a proof of principle for us that turned out nicely. We can go back now to protein expression, gene expression, whatever your data say with this PCPCA. Here's the original data set. This is with just probabilistic PCA. Here's with our gamma variable set to 0.9. I'll say this is just the foreground data. And what you see here is that opposed to before where the foreground data didn't separate very nicely, now the foreground data, the cases, the ones that have been treated with actually electric shocks, actually you see very distinct separation between these two groups. So DS is a particular type of disease that some mice have, the yellow ones, and non-DS are the mice that don't have this disease. You can see very strong separation in this contrastive model. And then if we project the case or the controls, sorry, with the gray points on here, you see that they're basically a little blob around 0 in both dimensions. That basically means that our factors don't explain variation in those in the controls very well at all, and that has to do with the likelihood minimization. So one problem with this, and this goes back to what we were talking about before with part-space representations and non-negative models, is that biomedical data often are counts. As we know in single-cell RNA sequencing, for example, we often just get counts of the number of reads that we identify in each of the cells that map to each of the genes that we have. So this is also a problem, or not a problem. The way data are represented in language and pixels and other things too. So we can actually extend our probabilistic contrastive model to non-Gaussian versions and a non-negative one in particular. So this is not the non-negative version. This is just the Poisson, the count version, where here our foreground data will be the combination of the shared variation right here and a foreground specific variation. And then background is just going to be the shared variation. And then actually we can just directly optimize this data, and then we can just look at this foreground specific variation as the solution, the contrastive solution here. So we actually applied this to some data from 2016 in Perturb-seq. So the idea behind Perturb-seq is that we have pooled CRISPR screens where we basically put a whole bunch of different CRISPR edits into a set of cells. And then we just do RNA sequencing on those set of cells where we can actually figure out which CRISPR edit was inserted into each cell. And then the foreground here is going to be the CRISPR treated cells, and the background is going to be the untreated cells. These are our controls. So one thing that we found with this count data, or this Poisson model, is that we can actually really nicely identify co-varying genes in a way that you can't do with simple linear models. So in this case, we have two different genes. This is LYZ2. This is just the log expression value here on the x-axis. The y-axis is CCL4. This is its log expression. And you can see that in the foreground data, there's a really nice relationship between the two of them. In the background data, there's none. It's just kind of astounding, actually. So when we just apply these linear models to them, we see that actually these two genes don't look like they're co-expressed at all in the foreground and background data, or just the foreground data. But when we use our contrastive Poisson model, we see that these two genes are now two of the top genes actually in this decomposition, because again, they're so strongly covarying only in the foreground data. Another type of structure that we were really interested in is spatial structure. Really what this means is now we have, a slice of a sample, and we can actually look at gene expression values for every single point, which might be a cell, which might be a set of cells in that sample. So here's an example from mouse hippocampus from SlideSeq V2, which is a single cell resolution method. And here's the expression levels of, one of whatever it is, 10,000 genes expressed in each of these, at each of these cells in the sample. So you can see a lot of spatial structure coming out here. So I'm going to skip over this because we kind of lack time. I'm just going to show you our spatial dimension reduction. This is called NSF, non-negative spatial factorization. And the idea here is that we have a fairly standard factor analysis model. Right here are our weights, and here are our factors. We're actually technically exponentiating our factors here as they are just a draw from a Gaussian process. The Gaussian process is what takes the data, which now is not just Y, our observations, but it's also X, which is going to be, in this case, a two-dimensional location associated with that, that observation, that vector of genes, gene expression levels. And so what our Gaussian process does in order to affect the factors, is basically says if we have 2 points, xi and xj, that are close to each other in this spatial coordinate system, then we'd like them to, in general, be in the same factor, okay? And then once we do that, we put everything through a Poisson. This is the non-negative part right here. We put everything through a Poisson, and that's how we generate each of the observations at each of the points, okay? Yeah, I'll just say very briefly that this ends up being a part-space decomposition. I'll show you what that means. And we use Matern kernels because not everything is as smooth as we want it to in these samples. I'm not going to talk about Gaussian process regression. I will show you what we do here. So here's a very simple simulation where this is the ground truth, and we can see a lot of different patterns here, spatially coordinated patterns. When we use factor analysis, like we see before, we get these really interesting, positive and negative real valued factors where there's some kind of combination of each of these sort of fundamental ground truth factors, or patterns. When we use non-negative methods, we actually see really nice separation of each of the 4 different components that we have here. And in fact, what we end up doing is a non-negative spatial and non-spatial factorization, which ends up cleaning up a lot of the disparate noise that we see in this sample. So this is the non-negative spatial factorization that involves both spatial and non-spatial factors that we end up using in the results I'm going to show you. So the first example is, again, the SlideSeq V2 data. These are single cell resolutions. It's a small field of view, but a very high resolution method. These are our factors that we find. We ran it with 10 spatial factors and 10 non-spatial factors. When I show you where these spatial factors are, these are just absolutely beautiful in terms of what they represent. So 2 of my favorites here are 8, which represents a dentate gyrase granule layer. You can just see it really coming out there very, very strongly. And my actual favorite is 10, the meninges, which is a very, very thin layer of cells that separates different brain regions in this mouse hippocampus sample. And the fact that it sort of fell out here was kind of astounding to me, actually. We also looked, because this was a non-negative model, there's a lot of sparsity. We looked at the top genes associated in the weights with each of these factors. And you can see that there are definitely spatial resolution, like here, you can see it very faintly, but it's not anywhere near as good as these, right? It's not nearly as distinct. And that really tells us that a lot of these brain regions, for example, are not necessarily identified with one or a handful of gene markers, where maybe you need a bunch of gene markers to be able to identify them appropriately. We can also look at the non-spatial factors from this model. Here's just two of them, where here we really obviously pull out astrocyte cells, and here we really obviously pull out neurons. But you can see that astrocytes and neurons are in general spread all over the hippocampus, with a few exceptions for astrocytes. These are both non-spatial. You can obviously see some spatial structure just based on differences in proportions of astrocytes and neurons, but in general, there's no spatial structure here. It's sort of scattered everywhere. Here's a second example that I can just show you. This is a very much higher, lower resolution, but higher field of view sample. This is from the mouse anterior sagittal section. And again, we see very, very nice definition of each of the different regions of the brain here. And as before, also, if we just highlight the top gene for each of these different brain regions, we do see a lot less structure, again, implying that even in this higher resolution or lower resolution setting, we do need multiple genes to mark these different these different brain regions. I'm not going to talk about this. I think I'm just going to talk about how to validate. So this is something that comes up a lot, and a lot of your questions have already asked these, to explain these ideas. But when we do dimension reduction, we need to validate the patterns we find, right? So the way that we do this is by using holdout metadata to sort of label each of the dimension reduction factors. We can use univariate tests for association when we think about like principal components analysis, or sorry, anything really where we have sets of genes that appear in the same factor with heavy weights. We can just look at how they're related to each other. We did this with the Poisson contrastive model, where you saw a very nice relationship between two genes. That's just a univariate test. We can also look at enrichment among the findings. So if we have a small set of genes that appear in a particular factor, we can do gene set enrichment analyses or look at co-expression to try and understand what it is about those genes that mean that they are sitting in this factor. Are they co-expressed? Are they have similar function? Are they a result of damaged lungs from smokers? So what exactly is it that puts these genes together? So at a high level summary, I just want to say that dimension reduction is generally, after processing the data, the first step in the analysis, but it is really hard to do well, and thought needs to go into it. There's so many methods to choose from. I think about what behaviors you want in the dimension reduction methods. Think about how you want to choose the number of latent dimensions. I generally try a whole bunch of them. And what held out data do you want to use to label those dimensions? What do you want to explain, or what signals do you want to explain in the variation of that data? And then finally, how do you explain the patterns that you've identified? How do you actually take those patterns out of the sample you're working with, your sort of data, and think about how to test them out of sample to be able to make something of them, to find discoveries and think about relationships that you couldn't see before. So that's the end. Here are all my students from a couple of years ago and collaborators, and I thank you for your time.
Thank you so much, Barbara. I don't know if you could hear the applause or not, but I swear there was. There is a question on Zoom that I'll mention quickly and then open it up to the room. So Siavash on Zoom asked for the PCPCA. Looks really cool. Was there a reason you didn't choose gamma equals 1 and instead chose gamma as 0.9? He said it seems like gamma less than 1 is required to get anything meaningful via optimization.
Yeah, that's exactly right. So it turned out that, I mean, having gamma as a tuning variable actually made a big difference in the data in terms of sort of, well, let me say it slightly differently. So here, gamma is 0.9, right? So there is a little bit of variation explained, right, in the background data, but it's not a lot. If we cranked it up to 1, then actually this would be literally just a point at 0, 0. Okay, like none of the background data would be explained at all. But this allows there to be a little bit of leakage at the expense of maybe a little bit of interpretability. So actually, we found that this being a parameter that you could tune actually made a lot of difference for us. And we actually have guidelines in the paper about how to set that gamma parameter. Yeah.
Great, thank you. Any questions in the room? I guess they've all been asked. Shirley?
I do have a quick question. I'm just curious the sparsity so that you went from PCA to non-negativity. And I do a lot of dimensional reduction before interpreting neural networks, right? So I'm curious if the assumption of non-negativity is actually super important, or is it, can you just replace it with L1? Or is it something that, like, assuming non-zero made that sparsity so more obvious?
Yeah, that's a great question. Oops. I don't know if I have an example of that. So the short answer is no. Part-space representation and sparse PCA or sparse factor analysis, or really any type of dimension reduction, end up giving you very different examples. So actually, where do I want to show you? Okay, here's a good example. So Mephisto here actually is a factor analysis with a spatial regularization, a Gaussian process, just like I showed you for our Poisson version, but it's not non-negative. And furthermore, there's a huge amount of sparsity. So this is actually L1 regularized components. So even though you can't see it actually, it uses a sparse number of features to describe each of these components, but they still look very, very different than the non-negative versions. Does that make sense?
Yes, she's nodding. Okay, anything else from anyone? No? Okay, I think they're hungry. Thank you so much, Barbara. This was incredible. Would you be able to send me your slides and I will pass them around to all the students?
Absolutely.
Awesome.
Mm-hmm.
Perfect. Thank you all so much. Thank you so much, Barbara.
Hello, everyone. Just a quick couple announcements. We do not allow eating or drinking here, except the speaker can drink water. So that's a special thing. Even Jim and Marilyn Simons don't violate that, apparently. So he's allowed to drink water. And we're very happy to have Yang Kun, the Meta Chief AI Scientist. Yes. And also very huge, NYU faculty with many names I don't understand. And I think Silver School professor, is that correct? Silver professor, yeah. And we're very happy to have him. And if you don't know who it is, you can take out your phone and Google for that one time. But otherwise, I'll let Yang take the stage. Thank you.
All right. Thank you, Shirley. Nice thing is I only have to walk 10 minutes to come here and give a talk. That's nice. All right, I'm going to talk about a number of different things, but the first half is going to be perhaps interesting for those of you who are new to machine learning and boring for those of you who are not. And then the second half might be the other way around. We'll see. So the first half is going to be about the basics and the present of kind of deep learning and AI today, and then the second half about the future or the challenges. So when we hear about AI today, that means we hear about machine learning, and that generally means we hear about deep learning, because a lot of applications of modern AI are based on deep learning, and most of those are based around supervised learning, which I'm sure many of you know what it is. So the basic idea of supervised learning is that you build a computer program, which is a mathematical function whose input-output relationship depends on a lot of parameters that are just numbers. So think of them as knobs on a panel, like this thing, and they modulate the input-output function, basically. So you train this machine by showing it examples. So you, for example, want to train a machine to recognize images of cars from images of airplanes. You show an image of a car, wait for the answer. If the system says car, you don't do anything. If it says something else, you adjust the knobs so that the outputs get closer to the one you want. Okay, it's as simple as that. And then you show an image of an airplane, adjust the knobs a little bit, car again, adjust the knobs a little bit. Then you keep doing this with millions of images. And eventually, if your machine is properly built, the knobs will settle on a configuration that can classify all the airplanes from all the cars in your training set. And the magic of it is that it will probably work also for images of cars and airplanes it's never seen before. That's called the generalization property. And this works really well if you have lots of data. But you need annotated data that's been annotated by people. So you can do things you can do this for speech recognition, for translation, for recognition, image recognition, or detection of objects in images and things like that. Classifying the topics of text, things of that type. And mathematically, it's formulated as an optimization problem. So basically, you come up with some sort of cost function that measures the divergence or distance or some measure of discrepancy between the output that the machine produces and the output you want. Okay, so X is the input, Y is the output you want, and then the cost is the distance between the predicted output and the real output. And for a particular training sample, that produces a number, and then you average this over your training set, that produces a number. Of course, you're going to have a different number for different settings of the parameters inside the machine. That is this vector W. So W is a long list of numbers that are the position of the knobs. And the way most deep learning systems work is that you do stochastic gradient descent, which means you show one sample, figure out in which direction and by how much to change all the knobs so that the cost goes down. Okay, so the discrepancy between Y and Y bar goes down. You make that change, and then you go to the next sample, adjust the knobs again. So the same process that I was talking about earlier, except now it's kind of formulated in terms of mathematics. So how do you figure out in which direction and by how much to change all the knobs? What you have to do is compute the gradient of that cost function. So basically, think of the cost function as some sort of landscape in the landscape of parameter values. And what you have to figure out is which direction should you take so that by making a small step, the function goes down by the largest amount. Okay, that's called the steepest descent. And that's given to you by computing the gradient of that function or the negative gradient of that function. That's what this direction is. So negative gradient is a vector, so it's at the bottom here, dl over dw. It's a vector whose dimension is the same as the number of parameters. And each component is the partial derivative of the function with respect to each of the dimensions, right? So you move in one direction, and you can compute by the slope in that direction by how much the function will go down, and then you have that for the second dimension. And if you are in a large space where you have 100 different knobs, then you have 100 different dimensions. So in each, you have a component. This gradient has one component for each of the dimensions. So you take a step in the negative direction of the gradient. The eta parameter is kind of a step size. And what you get is something similar to the diagram on the top right, where you get sort of a noisy estimate of the gradient on the basis of a single sample. Very often, for reasons of the limitation of our hardware, we don't compute the gradient on a single sample, but we compute it on a batch of samples, a mini batch of samples, and then compute the average gradient for that sample, and then take a step. So that's called stochastic gradient optimization. And it works amazingly well. It's very simple. I mean, there's all kinds of tricks to make it fast, but I'm not going to go into that. So then the next question is, what are we going to put in that box? This G of XW, what is it going to be? And that's where neural networks come in. So essentially what we want is some parameterized function so that when we adjust the parameters, the function can change from anything to anything. Like we can get it to approximate any function we want. And neural nets are a good way to do this. So what's a neural net? It's basically a bunch of computing elements, units, that we call neurons by analogy with neurons in the brain, but it's a very weak analogy. And what they do is they compute a weighted sum of their inputs. The weights in the weighted sum are the parameters that are adjusted. And then the weighted sum goes into a nonlinear function, generally something that has a kink in it, like the so-called ReLU. And that's like a basic neuron, a model neuron in a neural net. So you can have a bunch of those neurons looking at the inputs, and then a second layer, and then a third layer, etc. There are theorems that show that with just 2 layers, you can approximate any function you want, as close as you want, as long as you have sufficiently many units in the middle layer, in the first layer. But in practice, if you really want to learn complicated functions, you need many layers. So in fact, mathematically, you can represent this a little more abstractly. You can say, well, a deep learning system or a neural net, a modern version of a neural net, is really just a bunch of functional blocks, okay? So each of those boxes here is a function that takes an input, a set of parameters, and given input produces an output. The input and the output might be vectors or multidimensional arrays of some kind, let's say vectors for the time being. And to be able to train that system to compute the gradient efficiently, so you need to compute the gradient of the overall loss function with respect to all the parameters in the system. And that's done with the so-called backpropagation algorithm, which is nothing more than a practical application of chain rule. So the most complex mathematical concept on which deep learning is based is chain rule, right? It's very simple. Of course, it's kind of a sort of vector version of multidimensional version of chain rule, but it's the same thing. So the beauty of backprop is that it gives you some sort of recursive method to compute all the gradients of the loss function with respect to all the variables in the system in a single pass, whose cost is the same as the cost of computing the output from the input. So you don't have to tweak things to figure out in what direction should I tweak the knobs. You can just compute analytically what the gradient is. And so it's based on chain rule. The gradient of the loss with respect to the input to module I is going to be equal, so that's a vector, okay, whose dimension is the number of inputs to module I, is equal to the gradient of the loss with respect to the outputs of module I, which are the inputs of modules I plus 1, multiplied by the Jacobian, that's a matrix, of all the outputs of module I with respect to all its inputs, okay? So this matrix here indicates all the partial derivatives of every output of the module with respect to all of its inputs. And if you get the gradient of the loss with respect to the output of the module multiplied by the Jacobian, you get the gradient of the loss with respect to the input. This sounds complicated, but for things like weighted sums and nonlinearities, computing this is very, very simple. What's more, in modern deep learning frameworks like PyTorch, which some of you may have used, or TensorFlow or whatever, or JAX, you don't actually need to figure out how to do this, because you just write your function or describe the architecture of your network, and the system automatically figures out how to backpropagate gradients to compute the gradient with respect to whatever variables you want. So once you have the gradient with respect to all the inputs and the outputs of the modules, you can also using another Jacobian matrix compute the gradients with respect to the parameters, and it's the same formula really. So you have a second Jacobian because a function that has 2 arguments, there's 2 Jacobians with respect to each of the arguments. Very rarely do you have to actually compute those matrices explicitly, because the product of a gradient vector by the matrix can be done implicitly. So anyway, so there is a very useful machinery that does essentially automatic differentiation of complex functions that allows you to minimize the cost function, measuring the discrepancy of between the output you want from your system and the output it produces. That's what deep learning is, nothing more. Now, you can connect very complex functional blocks in all kinds of different ways, in complex graphs. It doesn't have to be like a neat stack of module. You can connect them in all kinds of ways. And that's what makes the power of deep learning. And it leads to kind of a new way of programming computers, where you don't actually write a program. What you write is the architecture of a deep learning system. And then with some data, you fine tune it so that it computes the function you want. Okay, that's called differentiable programming. That's what all of those JAX and PyTorch and TensorFlows do. Now, one question you might ask again is like, exactly how are we going to build those architectures, right, for neural nets? And one particular type of architecture is called convolutional nets, which is one of the things I'm famous for. And it's basically building the architecture of a neural net based on inspiration from that of the visual cortex in mammals. So there's some work like going back in the 1960s to the 1960s about like how neurons are connected in the visual cortex and what functions do they perform and things like that. And there were inspirations from that work to build neural nets even in the 1970s and 80s that could recognize images. So one of them is the so-called neocognitron model by Fukushima, whose picture is here in the center. And what I did in the late 80s, a few years after Fukushima, was to basically build a network of this type, more or less, but trained with backpropagation. Backpropagation only kind of surfaced around 1985, 86. So before Fukushima worked on his model. So that's an example of a convolutional net. You have an input image, and the first layer of units is not connected. Like each unit is connected to a local neighborhood on the input, so it only sees a little patch of pixels, if you want, and computes a weighted sum of those pixels, pass that through a nonlinearity, and that gives you sort of a activity in the units of the first layer. But then one trick in convolutional nets is that all the units within what's called a feature map share the same weights. So basically, whenever you have a unit in one part of the image that detects a motif, you're going to have another one in the other part of the image that detects the same motif because it's going to have the same weights. So that's called a convolutional layer, and it's very simple to implement. It's a special case of a linear layer. And so, basically multiple units share the same weights. It's called a convolutional layer because the operation performed by that layer is essentially a convolution or multiple convolutions. So so that's depicted on the bottom right, and I'm sure you've heard of some of that stuff. Many of you. Who has never heard of convolutional nets before? Don't be shy. Okay, because maybe it's very boring to you that what I'm telling you. Okay.
When to NERF's 1989? I'm just curious.
NERF's 1989. That was about 400 people.
Wow. Okay.
Okay. Now it's like what?
This is the NERF's paper 99.
8,000 now.
No, it was like 15,000. The meeting we went recently.
Okay, but that's virtual, so it's.
No, the one is still in person. 2019.
Oh yeah,
that was 15,000 people.
Well, the first NIPS was 1987, so this was the third. Right. So the first layer is a bunch of those units. They look at a local patch, and all the units in one of those maps share the same weights. And then you have multiple maps, each of which is basically detecting a different motif. Their weights are trained as part of backprop, right? So it's not hardwired. And then there's another type of operation here called pooling, which basically consists in computing the average or the max of the activities of a little patch of units in the first layer. And then, that's the output of a unit. And then you kind of take the next window, and if the windows are stepped by more than 1 pixels, that means the resolution of the pooled feature map is lower than the input. And then you repeat the process. You have convolutions again with nonlinearity, pooling, etc. That's a convolutional net. So that's an example of convolutional net in action. This is sort of vintage early 90s for recognizing handwritten digits. So the input is on the left, and then first layer, second layer, third layer. So convolution, pooling, convolution, pooling, convolution. And then by the time you get to the layer on the right, which precedes the output layer, you get a representation of the input that is very sort of distributed, kind of abstract, but also has a lot of invariance to it. So it doesn't change that much when you do things like translating the number 3 or distort it, which means that you're going to have a system that is able to recognize shapes independently of distortions and shifts and things like that, which is important for vision, but also for speech and other things. So that was relatively successful in the 90s, and my colleague and I, at the time at Bell Labs, built in New Jersey, built real character recognition systems that were actually deployed commercially and were reading checks and everything. But the research community lost interest in those models around the mid-90s, and it took almost 20 years for, like 15 years, for things to become popular again. So our friends from University of Toronto in Jeffrey Hinton's group in 2012 implemented a large convolutional net on using GPUs, which were becoming usable at the time and had been usable for a few years. And they built a very large neural net, much bigger than the one convolutional net, very much bigger than the ones we used in the past. Something with 1 billion weights in the system, or connections, I should say. And with this, they beat the record on the so-called ImageNet competition, which is a competition that computer vision scientists organized to test various techniques for recognizing objects in images. And the reason, and it worked much, much better than whatever it was that people were doing before, so much better than most of the computer vision community basically abandoned whatever it is that they were doing and sort of switched to using convolutional nets. And it happened extremely quickly. And I'd been sort of preparing the terrain with them with some other previous result, but they weren't convinced by mine. They were much, much better convinced by this one. So as a result, there's been like a huge amount of investment by industry and academia and government, et cetera, in AI research. That's basically what the reason we are hearing about AI so much in the last 10 years is because of this, okay? I mean, there are other successes also in, that preceded this actually in speech recognition and things like that, but really this was the watershed moment. And as a result, deep learning has been deployed in a lot of different situations now, and to the point that a lot of, it created a new industry. I'll come back to this, right? So there's a lot of applications, of course, in things like driving assistance. So you buy a car in Europe now, pretty much all the cars come with a little vision system that looks out the windshield. It's called an automatic emergency braking system. And if there is an obstacle in front of the car that the driver hasn't seen, the car will brake automatically to avoid a collision. And that reduces collisions by 40%, so it saves lives. And it's pretty much standard now in cars in Europe. A lot of cars in the US also come up of those things. The market is dominated by a company called Mobileye, which is a subsidiary of Intel, but was a extremely successful Israeli startup. And a huge amount of application in online safety and security. I'll come back to this, environmental monitoring and medicine and things like that. So for medical imaging, I'll come back to this. But probably the biggest application is in things like content management for online services. So things like, Facebook, Instagram, Google, YouTube, Amazon. They all use deep learning to filter objectionable content and to recommend content that are likely to interest their users. In fact, so much so that if you take deep learning out of those companies right now, they crumble. I mean, they're completely built around it in the space of 7 years, roughly 8 years. So going forward, deep learning will help us deal with the information deluge by, basically selecting pieces of information that are likely to interest us. The problem right now is that it's a little impersonal. It's done by some big company that, it seems like you're not in control, but eventually you'll have kind of more control over it. And then there's a lot of applications that those companies use for things like translation, transcription, generating subtitles in videos so you can watch them silently, and filtering content. I'll come back to this. Very useful for people who have who can't use technology because they can't read, for example, or because they are illiterate or they're visually impaired. So here's a short video that shows, it's a kind of an example of what computer vision systems can do today. This was put together by some of my colleagues at Meta. It's called Detectron 2, and it's actually open source. You can just download it. So computer vision systems can basically detect and label every object in an image. They can do real-time pose estimation of human bodies. This is a thing called dense pose, actually. And they can do things, something we call semantic segmentation, which means labeling every single pixel in the image with the category of the object it belongs to or the background surface. And this is quite reliable. It works kind of quite well. It runs really fast on like modern hardware. So if you kind of go back, 10 or 12 years in the past and ask people in computer vision, like, how long will it take for us to be able to do this with computer vision? They'll tell you, like, I don't know, 20, 30 years. It happened faster. Of course, a lot of applications in science. Actually, this is from one of your papers, Shirley. It's your PNAS paper from a few years ago, which I found really impressive. So a lot of applications in science, in neuroscience in particular, where people are using neural nets as a model of how the brain processes information, in particular for visual neuroscience, but also auditory perception, like speech perception, for example, where you take a convolutional net, which is vaguely inspired by the architecture of the visual cortex, and then using fMRI, functional MRI, you try to sort of predict the activity you observe in the fMRI observation from the activation of the units in a convolutional net that's been trained on ImageNet or something. And what you realize is that the lower layers in the convolutional net correlate very well with the primary visual cortex area where the retina projects. And then the higher you go in the levels, the more it correlates with things that are in the higher level areas of the visual cortex. So it seems to be like a good model of the visual hierarchy in the visual cortex. There are literally hundreds of papers on this now. And applications in things like high energy physics for detecting events, filtering trajectories of particles, and cosmology, and a lot of applications for like solving partial differential equations approximately but quickly, which is one of the big applications. So there are things where you want to, I don't know, design the blade of a helicopter or the foil of a flying sailboat or something like that. You need to be able to figure out the flow of the fluid on the airfoil and figure out the lift and the drag and all that stuff. And what you can do is train a neural net to predict those quantities from the shape without having to do all the expensive computational fluid dynamics. What you have out of this is a differentiable model that tells you from the shape what the properties will be. So now you can adjust it by gradient descent. You can tweak the shape automatically so that by gradient descent, it will give you exactly the characteristics you want. That's pretty amazing stuff. Similar things for like medical imaging. So this is a project that was a collaboration between NYU radiology department and FAIR. So by the way, FAIR used to mean Facebook AI Research, and now it means Fundamental AI Research. And it's part of Meta Reality Lab. So it's called Meta FAIR, maybe. And this is the idea in this project was, can we reduce the time we have to spend in an MRI machine by, say, a factor of 4 and still get images of the same quality by relying on deep learning systems to kind of recover the original image without loss of quality. And it turns out you can do that. So now instead of lying down in a claustrophobic, noisy machine for 40 minutes, you only need to spend 10 minutes. That reduces cost. It makes the exam cheaper and everything. So this was a open science project that was done, as I say, in collaboration between NYU and FAIR. And all the data set and results were published. And now the major manufacturers of MRI machines actually are implementing them in their machines. And Meta is not making any money out of this. This is all free. Not going into the details, but this is based on some ideas where you kind of rely on what you know about the physics of the process to kind of build the architecture of your deep learning system. And Shirley has been doing stuff like that too. I mean, a lot of people at Flatiron, I think. It's a bunch of publications on this that are really interesting. But there's something that is even more radical, and some people at NYU are working on this. Is the idea that we don't actually need to generate an image. Like, older man like me goes into a MRI machine to detect prostate cancer, for example. You need to generate 2D images for radiologists to kind of make a diagnosis. But in fact, we don't need to generate the images. We could just get the raw data from the machine, feed that directly to a neural net that would tell you, hey, yeah, this is prostate cancer or no, right? With obviously a very low rate of false negatives, which means you want the system to basically eliminate all the cases that are obviously not cancer, and then the ones for which there is a doubt, would be sent to a further exam, for example. So it's screening really. So Sumit Chopra at NYU is working on this idea. But the vision of the future of AI is a world in which, so 15 years from now or something, we won't be carrying smartphones in our pocket. We'll have something like augmented reality glasses, so glasses that can display information superimposed on the real world on screens that are in the glasses, have cameras looking everywhere, and microphones, and basically have a intelligent virtual assistant living in it, if you want. So I don't know if any of you have seen the 2013 movie, Spike Jonze movie, Her. It's kind of not a bad depiction of what could eventually happen with AI systems. In the movie, he falls in love with his virtual assistant. But this may be stretching a bit, but it's very likely. So you basically will have a virtual assistant that help you in your daily life, kind of like a human assistant a little bit, filter, help you sift through the enormous amount of information we're bombarded with every day, and etc. And tell you if you're about to cross the street and a car is about to run you over, it will scream at you because it has cameras, so it looks. And then, if you forgot your keys or your smartphone, it will tell you where it is. Well, you won't have a smartphone, but so that's a likely future. And the problem with this future is that we need AI systems that basically have human level AI for that. This assistant will need to have something close to human level AI. We also will want, domestic robots that takes care of all the chores in our house. That also requires close to human level AI. At least it requires some level of common sense of understanding how the world works that current AI systems don't have. And so the question is, how do we do that? Okay, that's the second part. And the first question we might ask is, how is it that humans and animals can learn so quickly? So take any teenager, most teenagers can learn how to drive a car in about 20 hours of practice. Most of the time without causing any accident, okay? Now, if you take one of the current learning methods to train a car to drive itself, you only have two choices: supervised learning. So supervised learning means you have thousands of people drive thousands of cars for thousands of hours, you collect all the data, and then you train a system to basically map a particular scene from the sensors, from the camera, to a particular action on the pedals and the wheels, right? That would be supervised learning. Or reinforcement learning. So reinforcement learning is that you have a car, you let the car drive itself, and when it makes a mistake, it detects that it makes a mistake, it gets punished, and it tries to kind of correct the strategy it used. You cannot do this in the real world. You have to do this in simulation, of course, because that would create tons and tons of accidents, kind of like this car here that runs off a cliff. So reinforcement learning, you would have, the car would have to drive itself for millions of hours, cause, hundreds of thousands of accidents, run off thousands of cliffs before it figures out that running off a cliff is a bad idea. And then another few thousand before it figures out how to not run off cliffs. And even then, it's not clear it will detect every cliff it's ever, that exists. It doesn't work. So obviously, the type of learning, supervised learning or reinforcement learning that we use currently is not sufficient to explain how humans and animals learn skills and learn so quickly. So we go back to, so this is a chart here that indicates roughly at what age babies, yeah.
You mentioned earlier how, like, in the 80s, some of the CNNs and stuff were inspired by biology, but the models you're talking about now seem like quite mathematical and statistical and quite divorced from, I guess, how a human would learn or a baby would learn. Do you think that will be something that comes back, like in the future, like this biological inspiration for how like a baby learns?
We'll come back. I'm sorry. Can you speak a little louder?
Sorry. You mentioned earlier that some of the earlier models were biologically inspired, but the more modern methods are quite mathematical.
No.
No?
I mean, not more, right? I mean, you look at like convolutional nets, for example, right? It's got this name, convolutional nets, so that sounds like mathematically sophisticated. But in fact, it's inspired by biology directly. Inside of it, you have those value units that are indirectly inspired by biology. You have things like something called layer norm, which is like a normalization of activities, among neighboring neurons. You actually observe this in V1. I'm not saying that people who came up with this idea were directly inspired by neuroscience, but there was some leakage of information between neuroscience and machine learning. The more recent stuff, like transformers, where you have basically gating mechanisms where certain connections are activated by activities of other neurons. This has been observed in neuroscience for decades. So the transfer of information from neuroscience to machine learning is not always direct and not always completely acknowledged by the people who use it, because they don't realize where those ideas come from, but they do come from neuroscience. And some ideas also are kind of more, originated by, from either engineering insight or mathematics, but that's rare actually. Right, so what type of learning do babies use? So this chart was put together by a colleague in Paris called Emmanuel Dupoux, who is kind of indicating at what age babies learn basic concepts about the world. So they learn things like distinguishing animate objects from inanimate objects, or figuring out that when an object is not supported, it falls. So the scenario here on the bottom left, if you show this scenario to a 6-month-old baby, where you put a little toy on the platform, you push the toy off the platform, the toy appears to float in the air, which is of course a trick. A 6-month baby barely pays attention. A 10-month-old baby goes like the little girl here, because in the meantime, she's learned that, unsupported objects need to fall, and this is violating her model of the world. So babies and animals learn models of the world in the first few weeks and months of life, and that this is the type of learning that we should be able to reproduce with machines, which currently we really aren't. Okay, I call this self-supervised learning. I'll come back to this in a second. But a lot is learned by babies and animals about the world, mostly by observation. In a few minutes of observation, probably you can learn that every object has a depth, because when you move your head, the best explanation for how your view of the world changes is the fact that every point in your world has a depth, a distance from you. That's the best way to explain how your view of the world changes when you move your head, or the difference between the view of your left eye and right eye. Okay, so notion of 3D probably occurs this way. Then the fact that you have this, distinct objects in the world is, probably due to the fact that you have occlusion edges. When you move your head, again, objects move differently from the background with parallax motion. So that, immediately sort of give you the concept of edges and objects and 3D objects, whose appearance changes when you change your viewpoint. And then on top of this, you can imagine building a whole hierarchy of concepts. There are objects that can move by themselves, animate objects, and then objects that just obey simple rules like gravity. They are predictable. The other ones are more harder to predict. Objects that don't move, and on top of this, you can build a very complex model of the world. Immediately, it tells you that I cannot just snap a finger and immediately appear 10 meters away. That's impossible because every example that you've seen in the world, except in Hollywood movies, tells you that objects move continuously and don't just disappear and reappear. So perhaps the source of what we call common sense is this ability to learn how the world works by observation. Of course, when babies, are a few months old, they start interacting with the world, and that also helps a lot. But initially, it's mostly just observation. So that leads me to the question of what are the next challenges for AI and machine learning? And the first challenge is learning those world models, like predictive models of the world. Allows us to fill in the blanks and predict what's going to happen ahead, and that's very important, as I'll say later. So I'm sort of advocating for something called self-supervised learning, which I'll talk about in a second. The second one is learning to reason. So neural nets, are basically input-output functions, so they don't reason really. Although some of the more complex transformer-type networks arguably are capable of some level of reasoning, but there's really no kind of deliberate reasoning of the type that we are used as humans, and even many animals can do. And being able to plan complex action sequences. So that led me to this analogy, which is what we can do at the moment is reinforcement learning and supervised learning, and those require supervised learning at least requires labeled data, labeled by humans, and so the amount of data that we can have is limited, and the amount of the number of bits that is provided by the labels given by human annotators is very small. It's a few bits per training sample. Reinforcement learning is worse. Although the reinforcement can be automatically generated by a machine, the amount of information provided for each trial in a reinforcement learning setting is extremely small, because you're only telling the machine whether it's good, whether its answer was good or bad. You're not telling it what the correct answer is. So if it's a small number of discrete actions like Atari games, that's fine. But if it's like a high-dimensional continuous space, it's super inefficient. So reinforcement learning requires a ridiculously large amount of trials compared to human learning. But when you can do this, it works really well. You can train a machine to play Go or chess or various games, and it works. It'll beat you, to a pulp. So it works really well when it works. But really, most of the learning that humans and animals do is this kind of self-supervised learning thing, which you train yourself to predict what's going to happen in the world by observation. And in fact, that's probably the main mode of learning that humans and animals perform. That's where most of the information we gather and we train our brains with comes from. And so if you do the analogy of intelligence and learning to appetizing cake here, the bulk of the cake is the self-supervised learning. Supervised learning is really the icing on the cake, and reinforcement learning is the cherry on the cake. And the analogy is with the amount of information you get from every sample. Okay. And so it's like we are in the same situation as physicists. Tell me if I'm wrong, Shirley. But basically, we can do the cherry, we can do the icing, but the rest is the dark matter of machine learning. So it's kind of like, in physics, we have no idea what dark matter is. And it's like, what, 60% of the mass of the universe? I mean, it's like more than that if you ignore dark energy, right? But so it's kind of this embarrassing situation where, like, most of the stuff that we should be interested in is unknown. Okay. So now let me try to make some progress in that direction. So let's say we want to build an autonomous intelligent system. So something that behaves a bit like an animal or a person. It will have to have a number of different modules. And this is my personal view of this. Not everybody in the field will agree with this. And this is a paper that I'm finishing that will probably come up next week if you're interested. There's also a blog post on Meta that explains this a little bit. But so basically, the centerpiece of that intelligent autonomous agent would be the world model. So something that enables the system to predict ahead what's going to happen in the world because the world is being the world, or because of the actions that the agent will take. There is the red module here is a cost module. So this is basically the entire goal of the agent is to minimize this cost. This cost is a cost function that produces a scalar value, and the scalar value is computed from the state of the world model. And the entire purpose of the machine is to take action so that the state of the world gets into a configuration that has low cost. And of course, you need a perception module to get an idea, an estimate of the state of the world beforehand. So there's two ways to use the architecture of this type. The first one is what I call mode one, by analogy with Daniel Kahneman's system one. So this is basically subconscious action. So you're, doing something you do all the time. You don't have to think about it. You don't have to plan ahead. You just reactively react. So X is an observation of the state of the world. You run this to an encoder that produces some representation of the state of the world, S of 0. That goes into some other, deep learning neural net thing, the actor, or the policy network, really, that produces an action in the world, and then, just keep doing this. You can measure the cost of the resulting state periodically. So that's sort of instinctive, reactive, intuitive action that doesn't require any planning. Now, if you need to plan a sequence of actions, things are a little more complicated. That's where you use your world model. So estimate the state of the world, you're using the perception module, and then run a predictor for a bunch of time steps that are going to predict what the state of the world is going to be, because the world is evolving, or because you take a sequence of action, A0, A1, etc. So you imagine a sequence of actions, you run your internal world model to predict what the result of the sequence of action is going to be. And then you measure the cost of the resulting state, predicted states, okay? And what you can do now, what the actor can do is essentially figure out a sequence of action that minimizes the cost given the prediction that are performed by the model. Okay, this seems, so this is actually very classical in optimal control theory. That's called model predictive control, and it's been around since the early 60s. With the difference that in optimal control, the model of the world is not learned. It's built by hand, a bunch of equations. Whereas here, we're going to learn this. So the cost can have some structure, which I'm not going to talk about. Actually, I'm going to say one word about it. So the cost is probably composed of two things. One is immutable intrinsic cost. So this is something that corresponds to like feelings of like pain and pleasure and hunger and thirst and things like that, right? So you have a piece of your brain called the amygdala that basically lights up when like an immediate thing happens to you, which is either good or bad, and it computes your degree of comfort or discomfort, essentially. And that part of your brain is basically immutable. That just determines human nature, right? So it's the thing that drives you to seek the company of other humans. It's the thing that drives you to be dominant or submissive, strangely enough, because we are social animals. We're like, chimpanzees or baboons. It's the thing that, when you're a baby, that drives you to want to stand up, so you learn to walk. The thing that drives you to want to have an effect on the world, like to grab stuff and move them. Okay, so all of those are intrinsic costs that kind of drive our basic behavior and our nature, and they're immutable unless you take drugs, which is very bad for you. And then there is another part called the trainable cost or trainable critic. And what the critic does is that it's trained to predict future values of the intrinsic cost. So, you know, you approach a cliff and you get a little bit of vertigo or you know, you're gonna get scared, you don't want to get too close because you know that if you get too close, there is a risk of falling, right? So there is a cost function that you train, you know, you train when you were a baby to like not get too close to a cliff. You probably fell off a bunch of small cliffs when you were babies, and that sort of trained this part of your cost. So it predicts ahead, right? For example, if I approach Shirley now and I pinch her arm, she'll be very surprised, and I'm not the type to do this, but you know, and then if the second time I approach, she'll probably be, you know, a little afraid and probably will, you know, recoil, right, or protect herself because you know she knows she got pinched the first time. So that's, you know, the predictive critic kind of predicting ahead that there is a possibility of pain going forward, right? So it's useful to have something that predicts ahead whether a situation is going to have a good or bad outcome, essentially. And this is the seat of emotions, essentially. So if an autonomous AI system has cost functions of this type, it will necessarily have emotions because they're basically anticipation of good or bad outcomes. You know, elation, fear, things like that. So, you know, the idea of, you know, a science fiction idea of commander data where, you know, there's an emotion chip that you can turn on or off. No, like if you have autonomous intelligence, you have to have emotions. Yes. No.
Yeah, I think the speak is on. Okay. So what I was gonna ask is how do you like sort of try to model the idea of like a choice? Like I get that you can model logical decisions, but there's like a lot of randomness whenever a human makes a choice, and naturally it's like based on the past data, whatever experience that person has, but still like two people with the same experience can possibly have like different choices, and that would like have a certain degree of randomness.
Yeah.
But with like artificial machine, you cannot like allow a large degree of randomness, so there are like lots of dangers with it. And I think, I'm not sure, like a lot of like the ideas of like bias in AI or whatever can be like sort of related to it, as in like for say credit card companies or whatever, if somebody is racist over there, then that's like a human's fault. But if like an AI model is biased, then it is the model's fault. But like say if a person was there, they could make a choice to not be racist despite having biases, and a model cannot make a choice independently because of some, like I don't know how would it deal with that randomness. And I mean, I don't really understand if we can control whatever harmful effects it could have.
Yeah, very good question. There is like 3 or 4 different questions that are completely unrelated in your question. Okay.
Yeah.
So the first question is, yes, the world is not entirely predictable, and so there are things that, you know, in this. In fact, I'm coming to this because that's a very important point in the rest of the talk. If you observe a state of the world and you're trying to predict what's going to happen next, there are many plausible things that may happen that are all, you know, plausible or possible. And the question is, which one is going to occur, and how do you plan a sequence of action if you don't know what's exactly what's going to happen? So, so humans are very good at figuring out that there are uncertainties in predictions in their world model, right? So, for example, if I take I don't have a pen on me, but if I put a pen on the surface here with my finger on it and I let go, you know that the pen will fall, but you can't determine in which direction it's going to fall. Okay, so there's some level of description where you can say the pen is going to fall, and we all understand what that means. But a finer grain of description, you cannot tell me exactly in which direction it's going to fall. So that's a level of uncertainty. We are absolutely terrible as humans in our ability to predict ahead multiple scenarios when there are lots and lots of different options, right? So you're playing chess. You can make a move, and then the opponent has a number of different moves they can make, and the branching factor is whatever it is for chess, 16 or something. Then your next move would be another branching factor times the number of possibilities that the opponent just could play, etc. There's an exponential growth of the possible configurations of boards starting from a particular configuration. And humans are very, very bad at actually exploring that tree systematically. And the reason, I mean, we know we're bad because machines are much, much better than us at this. Like, a $20 gadget can beat you at chess. It can beat me at chess. Maybe you're very good. I don't know. But and now Go, right? And other games, poker, all that stuff. So that's the uncertainty. Then the bias is a completely different question, which we can talk one-on-one after the talk, but it's such a vast question that I don't have time to address here. But it's unrelated, frankly. Okay, so how do we train and build a world model? So the problem is that if we have a deterministic prediction in a world model, we get blurry predictions because we don't know what's going to happen among all the possible options. So what you see here in this column here are predictions of a neural net predicting what the cars in a highway are going to do. And what you see is the predictions are like incredibly blurry because the system doesn't know if each car is going to brake or accelerate or change lane. Same here. This is, again, a neural net trained to predict video frames. And so it's observing 4 frames, and then it's predicting the next 2. And the predictions are super blurry because it doesn't know what's going to happen exactly in the world. And so it predicts the average of all the possible outcomes, which is not a good thing to do. So that's where this idea of self-supervised learning comes in. So we have a scenario where we observe a few frames in the video. We're trying to predict the next frames. So we observe a piece of an input, and we're asking a system to predict the rest. And it could be predicting the future, but it also could be predicting other things like, predicting the left from the right or the past from the present or things like that. And the best way to approach this is through the concept of energy-based model. So what is an energy-based model? So we cannot just have a function that takes X and predicts Y because there are multiple Y's, so it cannot be a single function, right? So the best way is to represent this through an implicit function. So basically a function that takes X and Y and gives us, tells us whether X and Y are compatible or incompatible, okay? High value of the energy if they are incompatible, low value if it's compatible. If Y is a good continuation of X in a video clip, then we get low energy, if not high energy. And then that allows, multiple Y's to be compatible with a single X. So how do we train this? The problem with training an energy-based model is that we need to shape the energy function that measures the compatibility between X and Y in such a way that it takes low values for training samples and high values for everything else. And there's essentially 2 classes of methods, one called contrastive method. So contrastive method consists in giving the system training samples and telling him the energy should be low for those training samples, and then generating fake samples called contrastive samples outside of the region of training samples, and then pushing their energy up so that the energy function takes the right shape. Okay, so that's the first category. And the problem with contrastive methods is that you need a number of contrastive points to be pushed up that grows exponentially with the dimension of the space. So at some point they're impractical. They're still fairly popular. You'll see a lot of papers on contrastive methods. What I prefer is things called regularized method. And what the idea there is you make the volume of space that can take low energy as small as possible using a regularization function that has some measure of that volume of space. I'm going to go to the jump to the skip to the chase. So there's a lot of self-supervised learning methods now that I can skip this that work really well in natural language processing, and they're a type of contrastive methods called denoising autoencoders. And basically, the idea is that you take a piece of text and you corrupt it by removing some words, for example, replacing them by a blank marker, and then you run them through a large neural net called the transformer architecture to predict the words that are missing. Okay, in the process of doing so, the system actually learns a lot about the structure of text. And subsequently, you can use this pre-trained system to the internal representation of text as input to a downstream task, like, I don't know, detecting hate speech, doing translation, or things of that type. This works really well for text, for speech recognition. You can train those systems to generate text. I don't have to go into this. But what's most interesting, I think, is something called JEPA. Okay, so this is joint embedding predictive architectures. And those are a particular type of architecture for self-supervised learning, where again, you feed an X and a Y. And you're basically telling the system, find a representation for X that represents as much as it can about X, and one for Y that represents as much as it can for Y. But at the same time, there is some a predictor network that can predict the representation of Y from that of X. Okay. So the system tries to find a trade-off between representing as much as it can about the world and then making that representation predictable in time. So for example, if we are here and I shoot a video with a camera panning, and X is the first few frames and Y is the next few frames, there's no way that a learning system will learn all the details of the texture of all of your hair, or the texture of the ground, or things like tiny details like this that are basically very difficult to predict. If you were in a landscape outside, there could be trees with leaves moving and a pond behind with ripples, and there is no way we can predict the details of this. So a lot of information needs to be eliminated that is really not relevant and difficult to predict. Basically, you call it noise. And then preserve the part of the information in the world that you can predict. And that is an abstract representation of the world. And that's what intelligence is about, really. It's constructing abstract representation that allows you to make predictions. So the method, my favorite method for this is called VicReg, actually here. And it's in the 20 seconds I have left. It's a method that basically attempts to measure the amount of information contained in SX and SY and tries to maximize it. And it does this by making sure each component of SX and XY has certain variance, so is not constant. And then by making sure the different components of SX and XY are decorrelated from each other or even independent of each other. Okay, I don't have time to go into the details of how this is done. You basically compute the covariance matrix of SX and XY over a batch, and you try to make it as close to the identity matrix as possible. And then simultaneously, you train a predictor to make predictions. And that works really well for things like learning features to recognize objects and things of that type, but I'm not going to bore you with details. So let me conclude. And so, by the way, this diagram, which I don't have time to explain, talks about like how do you plan hierarchically in the presence of uncertainty. So this connects to your question. So steps toward autonomous AI systems. So the future of AI systems will use self-supervised learning representations of the world, learning predictive models. Handling uncertainty in the prediction will be done probably by things like joint embedding predictive architectures, the JEPAs, which are explainable by this energy-based model framework, which you can't explain with probabilistic modeling. The systems will learn the world models by observation. They'll be able to reason and plan using this mode 2 technique I was explaining, probably hierarchically. I didn't have time to explain that. And then there's a bunch of kind of crazy hypotheses that one hypothesis here is that in our brain, in the human brain, we basically have one engine for simulating the world. It's in our prefrontal cortex. And we only have one. which means that we can only attend to a single task at a time. A single conscious, deliberate task that requires planning, we can only attend to one at a time because we only have one word model engine, predictive engine in our head. We can do a lot of subconscious tasks simultaneously. Like we can drive while we're talking to someone, but the driving has become subconscious. We don't need a world model for that anymore because we need it for talking to the person. And so that would be an explanation for why we can only attend to one task at a time. We only have one world model engine in our head. And it's configurable for the task at hand. So there is a need for this mysterious configurator module at the top that basically sets primes the entire system for the task at hand. How this is done is not clear to me. Thank you very much. Yeah, I have 31 seconds left.
Questions about having drinks over at the rooftop.
Fine with me.
So we're gonna have the internal receptions and also the reception to this talk at the 12th floor, the basic rooftop of 162. So let's take questions there. Let's thank you, Jan, again.